Hello there, and welcome to Science for Sleep, where we take complicated ideas, lower the lights a little, and explore them slowly enough that you can follow along without feeling as though there will be a test in the morning. Tonight, we're heading into our own cosmic neighbourhood to meet something very strange indeed. An object so faint that you could stare directly toward it with an ordinary telescope and see absolutely nothing. So small that it never managed to become a proper star, and so cold that parts of Earth can occasionally be warmer. Its name is WISE 0855-0714. Admittedly, that isn't the friendliest name in astronomy. It sounds less like a mysterious object drifting through space, and more like the password printed underneath a router. But hidden behind that collection of letters and numbers is one of the most unusual objects astronomers have ever found close to our solar system. WISE 0855-0714 is commonly described as the coldest known brown dwarf. And brown dwarfs are already strange enough before we start making them unusually cold. They form in much the same general way stars do, beginning with clouds of gas collapsing under gravity. But they don't grow massive enough to sustain the ordinary hydrogen fusion that powers stars like our Sun. They occupy an awkward region between stars and giant planets, sharing characteristics with both while fitting comfortably into neither category. WISE 0855 pushes that ambiguity to an extreme. Its temperature is only a few hundred Kelvin. Depending on exactly how astronomers estimate it, modern observations place it somewhere around the temperature range you might associate with an exceptionally unpleasant winter day, a very cold freezer, or something only modestly warmer than Jupiter. That is a remarkable thing to say about an object that formed through a process related to star formation. We are used to thinking of anything remotely star-like as hot, as our Sun has a visible surface temperature of roughly 5,800 Kelvin. Some stars are considerably hotter than that. Even many brown dwarfs glow with temperatures of hundreds or thousands of degrees. WISE 0855 is different. If you could somehow place it beside the Sun, which would be a terrible idea for several reasons, the contrast would be almost ridiculous. One is a brilliant sphere of plasma pouring energy into space. The other is a dark, cold object that has spent an enormous amount of time slowly giving away the heat it once possessed. And yet, WISE 0855 isn't hiding on the other side of the galaxy. It is practically next door. Astronomically speaking, at least. It lies a little more than 7 light-years from us. Light leaving it takes just over 7 years to reach Earth. That still amounts to tens of trillions of kilometers, so I wouldn't recommend adding it to tomorrow's travel plans. But compared with the scale of the Milky Way, it is remarkably close. Our galaxy stretches across roughly 100,000 light-years. Against that enormous distance, 7 light-years is the cosmic equivalent of discovering that a very strange neighbour has been living a few houses down the road and nobody noticed because they never turned the lights on. And for a long time, we really didn't notice. That may be the most interesting part of our introduction tonight. WISE 0855 is close. It is massive. It is probably around the size of Jupiter, as brown dwarfs generally remain roughly comparable to Jupiter in radius, despite often containing considerably more mass. And somehow, humanity went through thousands of years of watching the sky without knowing it was there. No ancient astronomer recorded it. No sailor navigated by it. No constellation includes it. You cannot step outside tonight, find a dark patch of countryside, allow your eyes to adjust, and point toward WISE 0855. Your eyes simply aren't equipped for the job. The object is too cold and too faint in visible light. Most of the energy escaping from something at this temperature comes out at infrared wavelengths, rather than as the visible light our eyes detect. In other words, WISE 0855 has not exactly been hiding. We simply spent most of human history looking at the universe with the wrong kind of eyes. Which raises a nice question for tonight. Where are you listening from right now? Maybe you're somewhere warm, with a window slightly open, and the remains of daylight still outside. Maybe you're somewhere where it is already well past midnight. Perhaps you're under a heavy blanket because the room is cold, or perhaps you're wondering why anyone would voluntarily think about freezing temperatures while trying to get comfortable. Whatever the temperature is where you are, imagine for a moment that only a little more than 7 light-years away, an entire world-sized object is drifting through interstellar space with no nearby star warming its atmosphere. No sunrise arrives there. No warm afternoon follows the morning. There is no summer. There may not even be a surface in the ordinary sense of the word. Instead, there is a thick atmosphere of hydrogen, helium, methane, water vapor, and other molecules surrounding an object whose deeper layers become hotter and denser as you descend. Somewhere inside, heat left over from its formation is still escaping, very slowly. That faint internal heat is almost everything astronomers have to work with. And if you find journeys like this soothing, interesting, or simply useful for giving your brain something calmer to think about while the day winds down, you can leave a like and subscribe to Science for Sleep. It helps these longer explorations find other people who enjoy learning about the universe at a pace that doesn't require sitting upright with a notebook. Although if you do have a notebook, I certainly won't stop you. Just try not to become too enthusiastic about brown dwarf atmospheric chemistry at 1 a.m. It happens. For now, get comfortable and consider how peculiar our neighbourhood already seems. We often imagine the space around the Sun as relatively well known. There are 8 planets. There are dwarf planets, moons, asteroids, comets, and a great deal of dust. Beyond the solar system, we can name the closest stars: Alpha Centauri, Barnard's Star, Sirius a little farther away. They can make the local region feel mapped, but a map depends on what your instruments are capable of detecting. For most of astronomy's history, telescopes were designed primarily to collect visible light. That makes perfect sense. Human eyes evolved to see visible wavelengths, and the Sun happens to produce enormous amounts of them. So when people built better eyes for themselves, they naturally began by building instruments that collected more of the light they could already see. That strategy revealed planets, nebulae, galaxies, star clusters, exploding stars, and objects billions of light-years away. But cold brown dwarfs presented a different problem. They aren't bright little stars waiting for somebody to point a larger telescope toward them. As a brown dwarf ages, it cools. Unlike a normal star, it does not have a stable hydrogen fusion engine continuously replacing the energy radiated from its surface. It begins warm because gravitational collapse and processes early in its life generated heat. Then, over immense spans of time, that heat leaks into space. The object grows dimmer, its spectrum changes. Molecules that would be destroyed at stellar temperatures can survive in its atmosphere. Eventually, if the brown dwarf is sufficiently low in mass and sufficiently old, it can become extraordinarily cold. WISE 0855 appears to have reached that regime. When astronomer Kevin Luhman identified it using observations from NASA's Wide Field Infrared Survey Explorer, or WISE, he wasn't simply finding another faint point among billions of faint points. He was identifying something that moved. That movement mattered. Imagine taking 2 photographs of the same crowded street several months apart. Most of the distant buildings would stay in exactly the same locations, but someone walking along the pavement would appear in a different spot. Astronomers can use a similar idea with the sky. Very distant stars and galaxies appear almost fixed over short periods. Nearby objects can shift noticeably against that background. WISE had observed the entire sky in infrared light, and within those enormous collections of data were objects whose positions changed between observations. WISE 0855 moved remarkably quickly across the sky, not because it was racing through the universe at some absurd science fiction velocity, but because it was close enough for its ordinary motion through space to become obvious against the distant background. It was the astronomical equivalent of seeing something move in the corner of your eye and realizing it was much nearer than you thought. Follow-up observations with the Spitzer Space Telescope helped astronomers measure another small apparent shift called parallax. Parallax is something you can demonstrate without leaving your bed. Hold one finger in front of your face and look at it with your left eye closed. Then switch eyes. Your finger appears to jump sideways relative to the room behind it. Obviously, your finger hasn't actually teleported. The apparent change happens because your two eyes observe it from slightly different positions. Earth gives astronomers a much larger version of the same trick. Observe a nearby object when Earth is on one side of its orbit around the Sun, then observe it months later when Earth has moved to another position, and the nearby object appears to shift slightly against much more distant background sources. Measure that shift carefully enough and you can calculate its distance. For WISE 0855, that calculation placed the object only a little over 7 light-years away. Suddenly, this barely visible infrared smudge wasn't merely an unusual cold object. It was one of our near neighbours. That fact still feels slightly surprising because distance in astronomy usually makes everything harder. A faint object thousands of light-years away is understandable. Its light has spread over a huge volume of space before reaching us. WISE 0855 is faint despite being close. It is almost impressively bad at being noticed. If it were a normal star at the same distance, it could be an obvious presence in our sky. Instead, WISE 0855 emits so little visible light that its discovery required sensitive infrared observations and careful comparison of images taken at different times. This is where the nickname Coldest star becomes both useful and slightly misleading. WISE 0855 is not technically a star. A proper main sequence star has enough mass for the pressure and temperature in its core to sustain hydrogen fusion. Hydrogen nuclei combine through nuclear reactions, releasing energy that can keep the star shining for millions, billions, or in the case of very small red dwarfs, potentially trillions of years. Brown dwarfs miss that threshold. They form in a star-like fashion, but end up without enough mass to keep ordinary hydrogen fusion going. The lower boundary becomes particularly interesting because objects with only a few times Jupiter's mass begin to overlap physically with giant planets. WISE 0855 has been estimated to contain only several Jupiter masses, although the exact figure depends strongly on its age and on models of how objects this cold evolve. That leaves us with an object that looks enough like a giant planet to make comparisons with Jupiter irresistible, yet appears to be wandering alone through space, without a parent star. If Jupiter were removed from our solar system and placed by itself between the stars, it would begin to resemble the general sort of object we're discussing. Not exactly. Jupiter is colder, has its own particular history and composition, and formed as part of our planetary system. WISE 0855 likely formed independently through processes more closely related to the formation of stars and brown dwarfs. But observationally, the comparison is extremely useful. For astronomers interested in giant exoplanets, WISE 0855 offers something rare. Normally, trying to study a cold giant planet around another star is rather like trying to photograph a moth sitting beside a stadium floodlight. The planet is faint. The star is overwhelmingly bright. Separating the planet's light from the star's light can be extremely difficult. WISE 0855 has solved that problem by having no bright star beside it. There is no nearby stellar glare drowning it out. It sits alone. That makes it a natural laboratory for studying an atmosphere at temperatures approaching those of giant planets. Of course, astronomers then encounter the next problem. The laboratory has switched most of its lights off. WISE 0855 is so dim that obtaining a detailed spectrum from it is difficult even with some of the most powerful telescopes humanity has built. A spectrum is one of astronomy's best ways of finding out what an object is made of. Instead of simply measuring how bright something appears, astronomers spread its light into different wavelengths. Atoms and molecules interact with particular wavelengths in recognizable ways, leaving patterns of absorption or emission. It is a little like receiving a barcode from a place you can never visit. Read it carefully enough, and you can begin to identify what is present. For warmer stars, collecting that light can be relatively straightforward. For WISE 0855, every photon is precious. The object emits strongly in parts of the infrared, and Earth's atmosphere itself absorbs many infrared wavelengths. Our own planet inconveniently contains water vapour, methane, carbon dioxide and other molecules that interfere with exactly the kinds of observations astronomers would like to make. Earth is very inconsiderate in that way. You spend billions building an enormous telescope, point it toward a fascinating atmosphere 7 light-years away, and our atmosphere gets in front of it. Putting telescopes in space helps enormously. That is one reason WISE 0855 has become such an interesting target for the James Webb Space Telescope. JWST was built to observe infrared light with extraordinary sensitivity. For an object that is cold, nearby, and almost entirely an infrared source, that is exactly what you want. Recent JWST observations have given astronomers a far more detailed look at WISE 0855 spectrum than was previously possible. And the atmosphere revealed by those observations isn't simply a colder version of the Sun. It is chemically much closer to the kinds of environments we associate with giant planets. Water vapour is present, methane is important, carbon monoxide has also been detected, and its presence tells astronomers something about movement inside the atmosphere. At the temperatures expected in the observable layers, basic equilibrium chemistry would predict certain proportions of molecules. But atmospheres aren't perfectly still chemistry experiments. Gas moves. Material can rise from warmer, deeper regions into cooler upper layers before chemical reactions have enough time to bring everything into equilibrium. So finding a molecule where simple equilibrium models suggest there should be less of it can provide evidence that the atmosphere is being mixed vertically. Even on an object this cold and dark, the atmosphere is active. That is worth keeping in mind. Cold does not mean dead. Dark does not mean simple. WISE 0855 isn't a frozen rock hanging motionless in space. It is a massive gaseous body with gravity, pressure, chemistry, circulation and internal heat. Its atmosphere may have clouds. For years, astronomers have been especially interested in the possibility of water clouds or water ice clouds forming there. That would be significant because water clouds are familiar to us on Earth, but much harder to study beyond the solar system. Earlier ground-based observations provided evidence interpreted as consistent with water clouds. Later, JWST spectroscopy showed that some of those spectral features could also be reproduced by cloudless atmospheric models, meaning the situation is more complicated than simply saying, "We found water clouds, case closed." Science rarely gives us the courtesy of making the first explanation the final explanation. Instead, researchers compare models, gather better observations, adjust assumptions, and occasionally discover that an exciting answer has brought along 3 new questions, which, fortunately, is how science remains employed. The atmosphere of WISE 0855 is especially useful because its temperature places it near a transition where substances familiar from planetary weather can begin condensing. Brown dwarfs come in different temperature classes, and the coldest known examples belong to a group called Y dwarfs. At higher temperatures, the atmospheres of brown dwarfs can contain clouds made from materials that sound rather alarming by Earth standards, including silicates and metals. Cool them enough and the chemistry changes. Different compounds condense. Methane becomes prominent. Eventually, temperatures can become low enough for water to condense. By studying a sequence of brown dwarfs from relatively warm examples, down to something like WISE 0855, astronomers can effectively watch atmospheric chemistry change across temperature. Not by watching one object cool in real time, of course. That would require a patience level beyond even this channel. Instead, they observe many objects at different temperatures and compare them, rather like reconstructing the stages of human aging by meeting people of many different ages, instead of following one person around for 90 years with a clipboard. WISE 0855 occupies one of the coldest ends of that sequence, and that brings us back to the basic oddity that makes it such a wonderful object to spend some time with tonight. we're only a few light years away from something that seems to blur the categories we usually rely on. Call it star-like, and it is much too cold and too low in mass to behave like an ordinary star. Call it a planet, and you immediately have to explain where its star went and whether it ever had one. Call it a brown dwarf, and you're using the technically appropriate category. But even then, WISE 0855 sits close to the planetary mass end of the population. Nature, as usual, did not read the labels before assembling the universe. Our categories are useful because they help us understand patterns. But the objects themselves simply follow physics. Gas collapses, gravity compresses it, temperature rises, perhaps nuclear reactions begin, perhaps they don't, heat escapes, atmospheres evolve, molecules form, billions of years pass. By the time someone on a small rocky planet happens to build an infrared space telescope and notices the result moving across a computer image, the object has no particular concern about whether we plan to place it in the star folder or the planet folder. WISE. 0855 has probably been moving quietly through our region of the galaxy for an enormous length of time. Long before humans existed, it was there. When the first people looked at the night sky, it was there. When astronomers first turned telescopes toward the heavens, it was there. When Newton was working out gravity, when Herschel discovered infrared radiation, when the first photographs of stars were taken, and when astronomers began realizing that the Milky Way was only one galaxy among many, this cold, nearby object remained almost entirely unnoticed. Not because it was impossibly distant, because it was faint in precisely the wavelengths we were accustomed to seeing. That is one of the useful lessons WISE 0855 offers before we even examine it in detail. The universe we see is not necessarily the universe that is there. Our senses provide a narrow sample. Visible light occupies only a small portion of the electromagnetic spectrum. Radio waves stretch to longer wavelengths. Microwaves and infrared fill other regions. Ultraviolet, X-rays and gamma rays extend beyond visible light in the opposite direction. Build instruments sensitive to one of those regions and the sky changes. Objects that looked empty suddenly become bright. Cold dust appears. Gas clouds become visible. Distant galaxies emerge. And occasionally something only 7 light-years away finally introduces itself. The discovery of WISE 0855 also suggests a slightly uncomfortable possibility. If an object this close remained unknown until the 21st century, what else is nearby that we haven't identified yet? Astronomers have made enormous progress cataloguing our local stellar neighbourhood, and infrared surveys have uncovered many previously unknown brown dwarfs. But the coldest and faintest members are also the easiest to miss. There could be other low-mass objects wandering relatively close to the solar system, emitting so little energy that finding them requires exactly the right telescope, wavelength, survey strategy, and a great deal of careful data analysis. That doesn't mean there's secretly another sun parked behind Neptune. Anything large and luminous would have announced itself quite clearly. We're talking about the quiet population, the objects that do not shine much, the leftovers near stars that spend their existence cooling in interstellar darkness. WISE 0855 gives us one confirmed example, close enough to study in unusual detail. And the more we learn about it, the stranger the word frozen starts to become. Its observable atmosphere may be cold by astronomical standards, but deeper inside, pressure and temperature rise dramatically. It still releases internal energy. Its atmosphere moves. Chemical material is carried between layers. Radiation fights its way outward before escaping into space. This isn't an oversized snowball. It is an entire atmospheric system operating under conditions that happen to be far colder than those of most star-like bodies we knew before surveys such as WISE began finding white dwarfs. And somewhere inside all of that sits the history of how the object formed. Was WISE 0855 born from the collapse of a tiny molecular cloud core, essentially attempting to become a star and failing because there wasn't enough material? Did its formation resemble the lower mass end of ordinary brown dwarf formation? Could objects with similar masses sometimes form around stars as planets, while others form independently? At these low masses, formation history becomes as important as present-day appearance. Two objects could have similar temperatures and masses while belonging to very different stories. One might have formed inside a protoplanetary disk beside a young star. Another might have collapsed independently from interstellar gas. Put them side by side billions of years later, and distinguishing between them may not be simple. Whys. 0855 therefore isn't interesting merely because someone attached the word coldest to it. Records are nice. Astronomy's full of them. Largest star, most massive black hole, fastest orbit, most distant galaxy, coldest brown dwarf. But records eventually change as instruments improve and new objects are discovered. The real importance of WISE 0855 is that its extreme temperature allows astronomers to study physics and chemistry in a regime connecting brown dwarfs with giant planets. It gives us a nearby target where questions about clouds, atmospheric circulation, molecular chemistry, vertical mixing, temperature, gravity and planetary mass objects can all be tested without the glare of a host star. And because it is nearby, we can return to it. Different telescopes can observe it. Better instruments can improve old measurements. New atmospheric models can be compared against the same object. What began as a faint moving point in infrared survey data has gradually become one of astronomy's best laboratories for understanding what happens when a star-like object cools until its atmosphere begins behaving more and more like that of a planet. So as you settle a little farther into wherever you're listening from, keep that image in mind. Not an artist's illustration with dramatic blue clouds or a glowing sphere conveniently lit from the side. Those pictures are useful, but nobody has taken a photograph showing WISE 0855 the way a spacecraft might see it from nearby. The more accurate picture is simpler, a very faint object, a little over 7 light-years from home, a few times more massive than Jupiter. Roughly Jupiter-sized, too cold to shine like a star, warm enough inside to continue releasing leftover heat, moving steadily across the background sky, almost invisible until infrared telescopes taught us how to notice it. And now that we have noticed it, the obvious question is how something that began its existence through a star-like process could end up becoming this cold in the first place. That question of how something could become so cold begins with another question that, at first, seems even simpler. How did we find it at all? WISE 085 5-0714 is nearby by astronomical standards, but proximity does not automatically make an object easy to discover. If anything, this particular neighbour had almost everything working in its favour if its goal was to remain unnoticed. It produces practically no visible light. It has no bright companion star drawing attention to it, and most of the energy that does escape from it appears at infrared wavelengths that human eyes cannot see. For centuries, astronomers could have pointed telescopes toward its location and found nothing that looked remotely like a nearby star. There was no faint red dot waiting patiently in an eyepiece. There was no dramatic glow. There wasn't even a suspicious little speck that someone could circle on a photograph and announce, "We should probably investigate that." To ordinary visible light astronomy, WISE 0855 was almost absent. Finding it required looking at the sky in a different way. That opportunity came from NASA's Wide Field Infrared Survey Explorer, better known as WISE. The spacecraft was designed to survey the sky in infrared wavelengths, allowing it to detect objects that may be dim or completely invisible to ordinary optical telescopes. During its original survey, WISE repeatedly photographed the sky, covering the entire celestial sphere and observing many regions more than once. That repetition would turn out to be crucial. Infrared astronomy works especially well for objects that are cool. Everything with a temperature above absolute zero emits electromagnetic radiation. Hot objects can radiate strongly at visible wavelengths. Cooler objects tend to release more of their energy farther into the infrared. You experience a very ordinary version of this every day. A person standing in a dark room does not visibly glow, neither does a warm cup of tea. But point a thermal camera at either one and suddenly there is plenty to see. The camera isn't creating heat that wasn't there, it is simply detecting wavelengths your eyes ignore. WISE did something broadly similar on an astronomical scale. Instead of asking only, what is shining brightly enough for us to see, it could also ask, what is warm enough to produce infrared radiation? That opened a door to a population of very cool objects, including brown dwarfs that optical surveys could easily miss. WISE 0855 was an extreme example. It was not discovered because it was bright. It was discovered partly because it refused to stay in the same place. In two WISE infrared images taken about 6 months apart in 2010, the faint source had shifted noticeably against the more distant background. When astronomer Kevin Luhman later examined the WISE observations, that movement stood out. NASA's account of the discovery says Luhman noticed the unusually fast-moving object in March 2013 and then began investigating it with additional data. This is where the discovery becomes less like finding a bright beacon and more like noticing somebody walking through the background of two photographs. Imagine taking a picture through your bedroom window tonight. There are distant buildings, perhaps a few trees, maybe streetlights, and someone walking along the pavement. Take another photograph a few seconds later. The buildings barely change position. The person has moved. You immediately know that the moving person is much closer than the distant background. Astronomers use the apparent motion of objects across the sky in a related way. Stars are not actually fixed. They orbit through the Milky Way, each following its own path. Our sun is moving as well, taking the entire solar system along for the ride. But because stars are extremely far away, their movement across our line of sight usually appears very slow. An object passing relatively close to us can show a much larger change in position. Astronomers call this proper motion. WISE 0855 had a very large one. In the original discovery analysis, its proper motion was measured at roughly 8.1 arc seconds per year. That may not sound terribly dramatic. 8 arc seconds is a tiny angle. You certainly wouldn't look into the sky and watch WISE 0855 visibly scooting along between the stars while you finish your tea. But to astronomers, that amount of motion is striking. At the time of discovery, it gave WISE 0855 one of the largest known proper motions among stars and brown dwarfs. Something faint was moving quickly across the celestial background, and that strongly suggested that it might be nearby. There was still an important distinction to make. High proper motion can tell you that an object deserves attention, but it does not automatically give you an exact distance. Something could appear to move quickly because it is close, or it could genuinely have a high velocity through space. To work out just how near WISE 0855 really was, astronomers needed another measurement. They needed parallax. We touched on this earlier, but the discovery of WISE 0855 is a particularly nice example of why parallax matters. Hold your thumb at arm's length. Close your left eye and look at your thumb against something farther away. Now close your right eye and open your left. Your thumb appears to jump sideways. Move your thumb closer to your face and repeat the experiment. The apparent jump becomes larger. Move it farther away and the jump becomes smaller. Nothing mysterious has happened to your thumb unless you've been doing very unusual experiments before bed. What changed was your viewing position. Your two eyes observe the nearby object from slightly different locations, while the distant background barely shifts. Astronomers can do the same thing using Earth's movement around the Sun. Instead of two eyes separated by a few centimeters, they can observe from locations separated by a substantial fraction of Earth's orbit. A nearby star or brown dwarf will appear to shift slightly against the much more distant background as our viewing position changes. Measure the size of that apparent shift, and geometry gives you the distance. For WISE 0855, observations from WISE and NASA's Spitzer Space Telescope provided the positions needed to measure that effect. The original discovery paper reported a parallax of about 0.454 arc-seconds, corresponding to a distance of roughly 2.2 parsecs, or about 7.2 light-years. 7 light-years. That changed the significance of the discovery immediately. Astronomers hadn't merely found another cold brown dwarf somewhere in the Milky Way. They had found one almost in our backyard. When the result was announced in April 2014, WISE 0855 was described as the fourth closest known star or brown dwarf system to the Sun, based on the distances known at the time. It was farther away than the Alpha Centauri system, the nearby brown dwarf pair WISE 1049-5319 and Barnard's star, but closer than many familiar stars that have been known for centuries. That creates a slightly embarrassing image for humanity. We had mapped galaxies millions and billions of light-years away. We had measured the expansion of the universe. We had photographed exploding stars. We had detected radiation left over from the early cosmos. And there, only about 7 light-years from home, was a large object we hadn't properly noticed. It is a little like producing a detailed map of another continent and then discovering that someone has been living quietly in the shed at the bottom of your garden. The reason, of course, wasn't carelessness. It was temperature. WISE 0855 was extraordinarily faint because it was extraordinarily cold. From the infrared brightness measured by Wise and Spitzer, combined with evolutionary models, Luhmann's original analysis estimated an effective temperature of only about 225 to 260 Kelvin. That corresponds roughly to -48 to -13 degrees Celsius. The same analysis suggested a mass of about 3 to 10 times that of Jupiter, depending on the object's age. Those numbers were astonishing for a brown dwarf. Before discoveries like this, brown dwarfs were often imagined as objects that were dim compared with stars, but still quite hot by human standards. Some are hot enough for their atmospheres to contain vaporized materials that would be solids on Earth. WISE 0855 was operating in a completely different temperature regime. Its estimated temperature overlapped with conditions found on our own planet. Not pleasant conditions, admittedly. You probably wouldn't pack sandals, but still, Earth-like temperatures in any sense were extraordinary for an isolated object formed outside the normal warmth of a planetary system. NASA's announcement compared its temperature with the Earth's North Pole. For an object whose formation was related to the same general gravitational processes that create stars, this was a startling result. It also helped explain why nobody had found it earlier. A brown dwarf at 1000 or 2000 Kelvin releases far more energy and is easier to identify. Cool it to around 250 Kelvin and the task becomes much harder. WISE 0855 was not only faint in visible light, it was faint even for an infrared source. Astronomers were working near the limits of what their instruments could detect. The discovery therefore depended on combining observations rather than relying on one spectacular image. WISE provided the original detections. Spitzer supplied additional infrared measurements and precise positions. The Gemini South Telescope in Chile was also used in follow-up attempts, helping researchers constrain how bright, or more accurately how incredibly faint, the object was at shorter wavelengths. The result was assembled piece by piece. There is something useful about remembering that when we hear the word discovery. Astronomical discoveries are often portrayed as sudden moments. Someone looks into a telescope, there is a gasp, a new world appears, everyone immediately understands what it is. Actual astronomy can be much less cinematic. WISE 0855 first existed as measurements, a faint source in infrared images, a position, then another position, a suspicious amount of motion, another observation, a comparison with earlier data, a model, a distance estimate, a temperature range. Confidence develops gradually. The discovery happens not because one image looks impressive, but because several pieces of evidence begin agreeing with one another. WISE 0855 is an excellent example, because visually there was very little to admire. The images that revealed it do not show an enormous sphere covered with dramatic clouds. They show a tiny point, in some observations barely that. What made the point remarkable was how it behaved. Between images it moved. Across observations taken from different locations in Earth's orbit, its position shifted through parallax. Its infrared colours were extremely unusual. Its brightness suggested an astonishingly low temperature. Those clues together told a story that no individual pixel could provide. The full designation, WISE J 0855 10.83-071442.5, came from the survey and its location on the celestial sphere. Astronomical names can seem unnecessarily intimidating, but there is usually a practical reason for them. When a survey discovers enormous numbers of sources, naming everything after mythological figures would become difficult surprisingly quickly. We would run out of gods, heroes, monsters, and probably patience. Coordinate-based names avoid that problem. WISE identifies the survey. The numbers encode the object's approximate position in the sky using right ascension and declination. The shorter form, WISE 0855-0714, is considerably easier to say repeatedly, which is fortunate for everyone involved. Its location places it in the direction of the constellation Hydra, but don't expect to find it by locating Hydra tonight. Constellations are patterns created by bright stars visible from Earth. WISE 0855 contributes absolutely nothing to that particular artwork. It is far too faint. If anything, its discovery reminds us that the familiar night sky is a heavily edited version of our actual surroundings. Our eyes show us the bright things. The nearby universe also contains objects that do not cooperate with human vision. Brown dwarfs, coal dust, faint red stars, dark planets, small bodies moving between stars. Some produce visible light reluctantly, others barely produce it at all. Once infrared surveys became sensitive enough, astronomers began filling in some of those missing pieces. WISE was particularly effective because it did not simply examine a few selected patches of sky. It surveyed broadly. That matters when you don't know where an object is hiding. If you're searching for something nearby but faint, you can't necessarily point a telescope toward the obvious place, because there may be no obvious place. You need coverage, you need repeated observations, and you need a way to recognize candidates among enormous amounts of data. Motion became one of the most useful clues. Nearby objects tend to shift more noticeably across the background. WISE 0855 practically introduced itself through that movement. Kevin Luhman had already been searching WISE data for nearby objects with high proper motions. In 2013, that work had produced another remarkable result. The discovery of the nearby brown dwarf binary WISE EJ 1049 15.57-531906.1, often called Lumen 16, at roughly 6.5 light-years away. The search demonstrated that infrared survey data still contained significant nearby objects waiting to be recognized. Then came WISE 0855, fainter, colder, and only slightly farther away. The first distance measurement was later refined. Additional Spitzer observations improved the parallax estimate, and subsequent work placed the object at roughly 2.2 to 2.3 parsecs, a little over 7 light-years from the Sun. The details shifted as better measurements became available, but the basic conclusion remained the same. WISE 0855 is extraordinarily close compared with the vast majority of known astronomical objects. That closeness gave astronomers an unusually valuable opportunity. A similar object 50 or 100 light-years away might simply be too faint for detailed study. At 7 light-years, WISE 0855 is difficult, but possible. Every improvement in telescope sensitivity becomes useful. Every new infrared instrument offers another chance to pull information from its weak low. That is why the discovery did more than add one object to a catalogue. It provided a target, and astronomers love a difficult nearby target. Once you know where something is, you can keep returning to it. You can measure its position more accurately. You can attempt spectroscopy. You can search different wavelengths. You can test atmospheric models. You can look for variability caused by weather patterns or rotation. You can ask whether clouds exist there. You can measure molecules in its atmosphere. Eventually, you can point an instrument such as the James Webb Space Telescope toward the same faint object that barely announced itself in older survey images and begin extracting chemical information from it. None of that was obvious from the first detection. Initially, the most important clue was simply movement. There is an enjoyable irony in that. WISE 085. 5 is often described in ways that make it sound completely inactive. Cold, dark, faint, lonely. Yet humanity found it because, from our point of view, it was moving too much to ignore. Its high proper motion separated it from the distant background and revealed that this unremarkable infrared source might be sitting much closer to us than expected. Even its name preserves the circumstances of discovery. WISE, an infrared survey, numbers describing where it happened to be when we noticed it. Nothing dramatic, just coordinates attached to a faint source that moved between observations. The announcement in 2014 also came with an intriguing uncertainty. At an estimated 3 to 10 Jupiter masses, WISE 0855 was so low in mass that researchers had to consider whether it might be something other than a conventionally formed brown dwarf. Could it be a giant planet that once orbited a star and was later thrown into interstellar space? Rogue planets are expected to exist. Gravitational interactions in young planetary systems can, in principle, eject planets entirely, leaving them to travel through the galaxy without a host star. A Jupiter-like object wandering alone would be extremely difficult to distinguish from a very low-mass brown dwarf if all you had were its current temperature, brightness, and mass. The difference might lie not in what it looks like now, but in how it was born. NASA's initial report acknowledged that possibility while noting that a brown dwarf interpretation was considered more likely. That uncertainty makes the object more interesting, not less. The universe is under no obligation to place a clear dividing line between a planet and a brown dwarf. We created those categories after observing the objects. Nature creates the objects first. Some brown dwarfs can have only a few times Jupiter's mass. Some planets can become several times more massive than Jupiter. One may form from the collapse of a cloud of gas. Another may grow inside a disk around a star. After billions of years of cooling, the two could begin to look remarkably similar. WISE 0855 sits close to that uncomfortable boundary. Its discovery therefore brought two surprises at once. There was an extremely cold object only a little more than 7 light-years away, and the object was so low in mass that even deciding exactly what sort of thing had been discovered required care. Further observations would be needed. Its motion had told us it was nearby. Its parallax had told us approximately how nearby. Its infrared brightness had told us it was exceptionally cold. Evolutionary models suggested only a handful of Jupiter masses, but none of those facts by themselves could show us the circumstances of its birth billions of years earlier. Astronomers had found the neighbour. Now they needed to understand the neighbour. That required moving beyond the simple question of where WISE 0855 was, and asking what kind of object could occupy this strange region between the familiar categories of stars and planets. A normal star keeps itself luminous through sustained nuclear fusion. A giant planet such as Jupiter forms in a planetary system and shines mostly by reflected sunlight while slowly radiating internal heat. WISE 0855 does neither of those things in the usual way. It is alone. It is massive enough to dwarf Jupiter in mass, yet nowhere near massive enough to behave like the Sun. It was probably born through a process closer to star formation, but it never accumulated the material needed to become an ordinary hydrogen-burning star. That failure, if we can call it a failure, is exactly what allowed it to become so cold. Without a long-lasting fusion engine replenishing the energy escaping from its atmosphere, It had only one direction to go over time: cooler, dimmer, harder to see. To understand that uncomfortable territory between stars and planets, it helps to begin with the part of the name that causes the most confusion. Brown dwarfs are not actually brown. If one were bright enough to see clearly with human eyes, its appearance would depend on its temperature, and warmer examples would tend to look deep red or orange rather than anything resembling the colour of chocolate. The word brown was introduced because astronomers needed a name for objects that were cooler and dimmer than ordinary red dwarf stars. It was a convenient label, and astronomy has been living with it ever since. The dwarf part is not particularly helpful either, because brown dwarfs are not simply miniature versions of normal stars. They are something stranger. A brown dwarf forms when gravity pulls gas together, much as it does during the birth of a star. A region inside a cold molecular cloud becomes dense enough to collapse. As material falls inward, gravitational energy becomes heat. The centre grows hotter and denser, and the young object begins contracting towards something that looks, at first, very much like the early stages of a low-mass star. Then mass becomes the deciding factor. A star such as the Sun has enough material pressing inward that conditions in its core eventually become extreme enough for sustained hydrogen fusion. Hydrogen nuclei combine into helium, energy is released, and the star settles into a long period during which nuclear reactions continually replace much of the energy escaping from its surface. A brown dwarf never reaches that stable condition. It simply does not contain enough mass. The precise hydrogen burning boundary depends on composition and other details, but it lies at roughly 75 to 80 times the mass of Jupiter. Below that region, the central temperature and pressure never become sufficient to sustain ordinary hydrogen fusion in the way a true star does. NASA consequently describes brown dwarfs as objects that form in a star-like way, but lack the mass required to maintain hydrogen fusion. This is why you'll sometimes hear brown dwarfs called failed stars. It is memorable. It is also slightly unfair. Calling a brown dwarf a failed star is rather like calling Jupiter a failed sun, or calling a bicycle a failed lorry. It assumes the only successful outcome was becoming something larger. Brown dwarfs can exist perfectly well for billions of years. They develop complicated atmospheres. They rotate. They produce weather. They can have magnetic activity. Some have companions. Some are companions themselves. They occupy their own population in the galaxy and behave according to their own physics. Nothing about the universe appears particularly disappointed in them. The important difference is that a brown dwarf has no long-term hydrogen fusion furnace keeping its temperature steady. That has an enormous consequence. It cools. A newly formed brown dwarf can be hot enough to resemble a very faint star. It may glow strongly in infrared light and, depending on its temperature, release some visible radiation as well. But once it forms, most of its life becomes a slow process of losing energy. Heat escapes into space. The interior contracts. More gravitational energy is released. The object continues radiating. Given enough time, it becomes cooler and dimmer. That means brown dwarfs do not have a simple relationship between mass and temperature. With ordinary main sequence stars, temperature gives you useful clues about mass. A massive blue star is very different from a small red dwarf, and its temperature is closely connected to the nuclear reaction supporting it. Brown dwarfs are more troublesome. A relatively massive but very old brown dwarf can cool until it has the same temperature as a younger, lower mass one. If you discover a brown dwarf and measure its temperature, you cannot immediately place it on a scale and read off its mass. You need to know, or at least estimate, its age. This is one reason estimates for WISE 0855's mass span a range rather than producing one tidy number. Its present brightness tells astronomers how much energy is escaping now. Evolutionary models then ask what combinations of mass and age could produce an object this faint and this cold. A younger WISE 0855 would generally need to be less massive. An older one could be more massive and simply have had more time to cool. Studies of the coldest Y dwarfs have placed Ys 0855 in the planetary mass regime, with model-dependent estimates extending from only a few Jupiter masses upward. One detailed analysis using mid-infrared data found plausible values of roughly 1.5 to 8 Jupiter masses over a wide possible age range, and this is where the tidy boundary between brown dwarfs and planets immediately starts causing trouble. Jupiter is a planet. WIC 0855 may be only several times more massive than Jupiter, so why call one a planet and the other a brown dwarf? There are several possible answers, and astronomers have spent a great deal of time discussing them. One approach uses mass. Objects above a certain mass can briefly fuse deuterium, a heavier form of hydrogen. The traditional dividing line associated with deuterium burning is around 13 Jupiter masses, although the exact value changes depending on composition and how the definition is applied. Under a strict mass-based system, something below that boundary could be called a planet, even if it were floating alone through space. That sounds simple until you find an object that formed exactly like a star, but happens to contain 12 Jupiter masses. Has it become a planet merely because it missed an arbitrary nuclear threshold? Another approach focuses on formation. Planets form in disks of gas and dust surrounding young stars. Brown dwarfs form through gravitational collapse more like stars do. Under that definition, mass isn't the main issue. An independently formed object with 8 Jupiter masses could still be considered a brown dwarf, while a 15 Jupiter mass object that grew inside a planetary disk might be considered an unusually massive planet. NASA has highlighted exactly this problem when discussing low-mass companions. Two objects of similar mass may receive different labels depending on how they formed. Unfortunately, formation history is not something an old object carries around on a convenient identification card. Imagine finding an isolated gas giant several billion years after its birth. Perhaps it formed alone when a small cloud collapsed. Perhaps it formed beside a star, spent a few million years orbiting peacefully, and was then thrown out after a gravitational encounter with another planet. Today, both histories could leave you with a cold, Jupiter-sized object moving through interstellar space. One is a low-mass brown dwarf. The other is a rogue planet. Ask the object which one it is, and you will receive the usual response from astronomy: several years of telescope proposals. Ys 0855 sits uncomfortably close to this problem because it has such a low estimated mass. Its present properties resemble those expected for a giant planet in several important ways, particularly its temperature and atmospheric chemistry. Yet it is isolated, and the usual interpretation is that it belongs to the extremely cold end of the brown dwarf population. That alone makes it useful. But before reaching the unusual Y dwarfs, we should travel through the warmer members of the family, because brown dwarfs change dramatically as they cool. Astronomers classify stars largely by examining their spectra. Pass a star's light through an instrument that separates it by wavelength, and different atoms and molecules leave recognizable patterns. Those patterns reveal temperature, chemistry, pressure, and other properties. The same principle works for brown dwarfs, although the chemistry becomes considerably more complicated as temperatures fall. The familiar stellar sequence includes the letters O, B, A, F, G, K, and M. Our Sun is a G-type star. The smallest and coolest ordinary hydrogen-burning stars are M dwarfs. Once astronomers began discovering objects even cooler than the lowest temperature M dwarfs, the old sequence needed expanding, so new letters were added. L, then T, and eventually Y. This may sound as though someone organising the alphabet became tired halfway through, but the categories correspond to major changes in the spectra and atmospheres of these objects. L dwarfs are relatively warm by brown dwarf standards. Many have temperatures well above 1000 Kelvin. Their atmospheres can contain clouds made from mineral condensates. Materials that are ordinary rocks on Earth can exist as tiny particles in atmospheric clouds because the temperatures are high enough for unusual chemistry, but cool enough for some refractory compounds to condense. There can be silicate clouds. Iron can condense. The phrase chance of molten iron clouds would be alarming in an Earth weather forecast, but brown dwarfs have different standards. As an L-dwarf cools, those cloud layers change. Eventually the object may enter the T-class. Methane becomes increasingly important in its spectrum. Water vapour is prominent. The mineral clouds that strongly affect warmer brown dwarfs sink deeper, break apart, or become less influential in the atmosphere we can observe. The spectrum changes dramatically, even though the object's basic size may hardly change. Observational and theoretical work on L and T dwarfs shows how strongly clouds, gravity, molecular absorption, and atmospheric chemistry shape their infrared appearance. Cool the object still farther and you reach the Y dwarfs. This is the regime where Ys became particularly important. Before sensitive all-sky infrared surveys, astronomers knew that extremely cold brown dwarfs should exist, but finding them was difficult for the obvious reason that they were extremely cold. Ys was able to identify a population whose infrared colours and spectra extended beyond the known T dwarfs. Astronomers formally introduced the Y spectral class for these colder objects, and Y's discoveries helped establish what that class looked like observationally. A Y dwarf can have a temperature measured in only a few hundred Kelvin. Now we're no longer discussing an object merely cool compared with a star. We are approaching temperatures familiar from planets. At those temperatures, the atmosphere starts behaving in ways that make comparisons with Jupiter and giant exoplanets unavoidable. Water, methane, ammonia, hydrogen, cloud formation, chemical reactions affected by vertical mixing. All of these become part of the discussion. The distinction between stellar astronomy and planetary science begins to feel less useful. A researcher studying a hot brown dwarf may spend much of the time thinking like a stellar astronomer. A researcher studying WICE 0855 can find themselves discussing the same atmospheric molecules, cloud processes and circulation problems that planetary scientists study in giant planets. The object hasn't switched categories halfway through its life. It has simply cooled until the physics that dominates what we observe has changed. There is another odd feature of brown dwarfs that makes this transition possible. Their sizes do not increase in the simple way you might expect as their masses increase. You might imagine that an object 70 times the mass of Jupiter must be vastly larger than Jupiter. It isn't. Brown dwarfs remain roughly around Jupiter's radius, across a surprisingly large range of masses. Add more mass and gravity compresses the interior more strongly. At these enormous pressures, the material behaves in ways that are very different from an ordinary gas in your kitchen. Electrons are forced into a highly compressed quantum state, and electron degeneracy pressure becomes important in resisting further compression. The result is counterintuitive. A brown dwarf can contain dozens of times Jupiter's mass while remaining close to Jupiter in physical size. So picture Jupiter. Now imagine packing far more matter into roughly the same diameter. Surface gravity rises dramatically. Pressure inside becomes enormous. But the object does not expand into something remotely resembling the Sun. A brown dwarf can be star-like in its formation, planet-like in radius, and something else entirely in its energy source. This is why trying to describe one with a single comparison usually fails. Big planet gets part of it. Small star gets another part. Neither tells the whole story. There are even temporary episodes of nuclear fusion in some brown dwarfs, which complicate the phrase failed star further. Objects above roughly the deuterium burning threshold confuse deuterium early in their lives. More massive brown dwarfs can also destroy lithium. But these nuclear reactions do not provide the long-lived energy source that ordinary hydrogen fusion supplies to main sequence stars. The fuel is limited. The nuclear activity fades. Cooling continues. A sufficiently massive brown dwarf may therefore have experienced genuine nuclear fusion without ever becoming a normal hydrogen-burning star. NASA descriptions of brown dwarf interiors emphasize this short-lived deuterium-burning phase and the later cooling that follows. This gives astronomers a useful test in some cases. Lithium can survive in lower mass brown dwarfs because their cores never become hot enough to destroy it efficiently. In more massive objects, lithium is depleted. Looking for lithium in a spectrum can therefore help constrain the mass and nature of some brown dwarfs. It is a clever method, although unfortunately not especially helpful when your object is as cold and faint as WISE 0855 and refuses to provide a convenient bright optical spectrum. WISE 0855 tends to make every observational technique work harder. Its extreme temperature means most of the radiation escaping from it appears in the mid-infrared. At visible wavelengths, there is almost nothing. Even in parts of the near-infrared where many brown dwarfs can be studied effectively, WISE 0855 is exceptionally faint. The object sits at the end of a long cooling sequence where the atmosphere itself blocks much of the radiation, trying to escape at certain wavelengths. Molecules absorb specific bands. Other wavelength regions allow more radiation through. The final spectrum is not a simple, smooth glow. It is shaped by the atmosphere above the deeper, warmer layers. That means the light reaching us carries information. Very little light, admittedly, but useful light. Every absorption feature can reveal something about which molecules are present. The overall spectral shape can constrain temperature. Differences between observations and atmospheric models tell researchers when assumptions about clouds, chemistry, or circulation may be incomplete. The coldest white dwarfs have already shown that simple equilibrium models are not always enough. Studies comparing observations with models find that non-equilibrium chemistry and vertical mixing can be important, particularly because gases can be transported between hotter and colder atmospheric layers before chemical reactions fully adjust to the new conditions. This makes brown dwarfs unusually convenient test objects. Unlike giant exoplanets, many brown dwarfs are isolated. There is no brilliant parent star sitting beside them in the telescope image. That removes one of the hardest problems in exoplanet science. Consider trying to study Jupiter from many light years away while the Sun is in the same image. Jupiter would be extraordinarily faint compared with the star. Separating its light from sunlight would require very careful observations. Move Jupiter away from the Sun and allow it to drift alone through space, and it becomes easier to isolate its own thermal radiation. It would still be faint, but at least the floodlight has been removed. Brown dwarfs therefore allow astronomers to study giant planet-like atmospheres under relatively clean observational conditions. They are not perfect substitutes for exoplanets. A brown dwarf's gravity may be much stronger. Its formation history may be different. Its composition and internal structure can differ. A planet orbiting close to a star also receives external radiation that can dramatically alter atmospheric temperature and chemistry. WISE 0855 receives no meaningful warmth from a nearby star. Its energy comes almost entirely from within. That gives us something closer to a controlled experiment. Take a massive gaseous object, remove stellar heating, allow it to cool for an extremely long time, then observe what its atmosphere becomes. For WISE 0855, the result is an atmosphere with temperatures low enough that water condensation becomes possible under certain conditions. This is an extraordinary change from the hotter brown dwarfs where clouds may contain silicates and iron. Imagine following one object through its entire cooling history. Early on, its atmosphere is extremely hot. Over time, different materials condense as particular temperature thresholds are crossed. The visible cloud layers change. Spectral features change. Molecules that could not survive at higher temperatures become abundant. Methane strengthens. Eventually, in the coldest regimes, water can move from being merely a vapor to potentially forming cloud particles. The weather chemistry changes simply because the object keeps losing heat. We cannot watch that transformation happen to one brown dwarf from beginning to end because it takes far too long. Human civilization has not been running a continuous brown dwarf weather station for several billion years. So astronomers do the next best thing. They find many brown dwarfs at different temperatures. Warmer examples show one atmospheric regime. Cooler examples show another. The sequence allows researchers to reconstruct how these atmospheres change as substellar objects age. L dwarfs provide one set of conditions. T dwarfs continue the cooling sequence. Y dwarfs push into the coldest known territory. Ys 0855 sits beyond even most Y dwarfs in temperature. That makes it less like one ordinary member of a class and more like the extreme end of a natural experiment. This is also why discovering additional objects like it matters so much. One Ys 0855 can tell us a great deal. 10 objects at similar temperatures but different masses, ages and compositions could tell us much more. Astronomers could compare cloud behaviour. They could look for differences in methane and water absorption. They could test how gravity affects atmospheric circulation. They could see whether Ys 0855 is typical of extremely cold brown dwarfs or simply a particularly unusual individual. At the moment, the difficulty is finding them. The colder a brown dwarf becomes, the less energy it releases. The less energy it releases, the smaller the volume of space within which our telescopes can detect it. There may be large numbers of very cold brown dwarfs in the Milky Way that are simply too faint for current surveys to identify at great distances. We mainly discover the nearby ones. That creates an interesting bias. The coldest known brown dwarf may not be the coldest brown dwarf that exists. It is the coldest one we have managed to find and characterize. Somewhere in the galaxy, there could be older or lower mass objects that have cooled even further. There may be bodies whose temperatures approach those of the outer planets of our solar system. There may be objects drifting through dark regions between stars that radiate so weakly that even modern infrared telescopes struggle to notice them. Ys 0855 happened to be close enough. 7 light years is what gave us the opportunity. Move the same object 10 times farther away, and its already feeble signal would become drastically harder to measure. Move it across the galaxy, and it effectively disappears from our present view. So the strange world of brown dwarfs is partly a story about what we can detect. For centuries we classified the heavens according to the objects bright enough for us to see. Stars were obvious. Planets around our own sun were obvious. The things between those categories remained hidden until infrared astronomy became sensitive enough to reveal them. The first confirmed brown dwarfs arrived only in the 1990s, despite being members of a population that must have existed throughout the history of the Milky Way. Then surveys improved. L dwarfs multiplied. T dwarfs appeared. Ys revealed colder Y dwarfs. Each step pushed farther away from ordinary stellar temperatures and closer to the temperatures of planets. And eventually, among those infrared detections, there was Ys 0855, an object with roughly the radius of Jupiter. Only a handful of Jupiter masses according to many models, no sustained hydrogen fusion, no parent star providing warmth, an atmosphere cool enough to contain chemistry more familiar from planetary science than from ordinary stars, and a temperature low enough that describing it as a star, even casually, begins to sound increasingly strange. The remarkable thing is that Ys 0855 did not suddenly become cold. Its present condition is the consequence of its entire history. At birth, gravity compressed it and filled its interior with heat. From that point onward, it had no permanent stellar furnace capable of holding the cooling process back. Energy escaped through the atmosphere. The interior gradually changed. Its spectrum shifted as molecules and clouds responded to lower temperatures. The once warmer object moved through the brown dwarf sequence until it arrived at the extreme state we observe today. That leaves us with a very practical question. If brown dwarfs begin warm and then spend their lives cooling, how long does it take to reach something like Ys 0855? And what exactly happens inside an object with several times Jupiter's mass, while billions of years of stored heat slowly leak away? An object born through a star-like collapse, then, does not necessarily remain star-like forever. The important question is what happens after the gas has fallen together, the young object has heated up, and gravity has finished doing most of the dramatic work. For a true star, this is where nuclear fusion eventually takes over. For WISE 0855-0714 it never did. That single difference explains much of what followed. Imagine a large cloud of cold molecular gas beginning to collapse. Gravity pulls material inward from every direction. As the gas falls, it speeds up. Collisions between particles convert some of that motion into heat, and the center of the forming object becomes increasingly hot and compressed. Nothing needs to be burning in the ordinary sense. The heat is being generated by collapse itself. A useful everyday comparison is a bicycle pump. If you cover the outlet and compress the air inside quickly, the pump becomes warmer. Squeezing a gas raises its temperature because energy is being concentrated into a smaller volume. Now replace your bicycle pump with several Jupiter masses of hydrogen and helium, remove the handle and let gravity do the squeezing. The result is considerably more impressive. A newborn brown dwarf can therefore begin its life very hot, even though it has no permanent hydrogen fusion engine. Its original heat comes largely from gravitational collapse and contraction, together with the thermal energy stored in the material from which it formed. For a while, that's enough to make the young object glow strongly. But there is a problem. Heat escapes. Radiation leaves the atmosphere and travels into space, carrying energy away. If nothing replaces that energy at the same rate, the object must gradually cool. A normal star solves this problem with sustained hydrogen fusion. Deep in the Sun, hydrogen nuclei are continually being converted into helium. A small fraction of mass becomes energy, and that energy eventually works its way outward before escaping as sunlight. The Sun is losing energy too. It simply has an enormous nuclear power source replacing it. WISE 0855 never acquired that luxury. Its estimated mass is far below the roughly 75 to 80 Jupiter mass region needed to sustain ordinary hydrogen burning, so its evolution is dominated by cooling rather than by a long, stable period of stellar fusion. Brown dwarfs consequently grow cooler and fainter as they age. This sounds simple enough. No fusion. Heat escapes. Object gets colder. But brown dwarfs rarely allow us to finish an explanation quite that quickly. For one thing, cooling does not mean that the entire object has reached the temperature measured at its visible atmosphere. When astronomers say WISE 0855 has an effective temperature of around 250 to 285 Kelvin, they are describing the temperature corresponding to the amount of radiation escaping from the object as a whole. Recent JWST spectroscopy has produced atmospheric fits near 285 Kelvin, while estimates based on luminosity and evolutionary models can be roughly 20 Kelvin lower. That is around room temperature at the warmer end, which sounds almost comfortable. It isn't. If you were somehow placed near the level in its atmosphere associated with that temperature, you would not be standing in a pleasantly mild room wearing slippers. There would be no solid floor. The atmosphere would be dominated by hydrogen and helium, with enormous pressures deeper down, unusual chemistry, strong gravity, and absolutely no breathable air. The estate agent would have some work to do. More importantly, the interior is far hotter than the temperature astronomers infer from the radiation escaping into space. WISE 0855 is cold on the outside because its outer atmosphere has cooled dramatically. Go deeper and pressure rises, so does temperature. Far below the observable clouds and molecular absorption layers, the object still contains a large reservoir of internal thermal energy. That reservoir is slowly leaking away, and slowly is doing quite a lot of work in that sentence. Brown dwarfs can cool for billions of years. They do not suddenly go from glowing young objects to WISE 0855 temperatures over a quiet weekend. Their enormous masses mean they contain enormous amounts of stored energy, and their atmospheres regulate how quickly that energy can escape. The atmosphere is therefore more than a decorative outer layer. It acts as the boundary through which the interior loses heat. Molecules such as water, methane, ammonia, hydrogen, and carbon monoxide absorb radiation at particular wavelengths. Clouds can block or redistribute radiation. Convection carries heat upward through deeper layers. Radiation becomes more important in other regions. The precise atmospheric chemistry affects how efficiently the whole object cools. In that sense, the clouds and molecules we observe today are connected to the entire thermal history of WISE 0855. They help determine what energy can escape, and the escaping energy determines how quickly the interior cools. A brown dwarf is therefore engaged in a very long negotiation between gravity, heat, pressure, chemistry, and radiation. Gravity would like to compress everything. Pressure resists, heat moves outward. The atmosphere decides, rather inconveniently, that some wavelengths may leave more easily than others. Space accepts whatever eventually gets out. At first, contraction itself provides another source of energy. As the brown dwarf loses heat, pressure inside changes and gravity can squeeze the object slightly further. Gravitational potential energy is converted into thermal energy during this contraction. This general mechanism is related to what astronomers call Kelvin-Helmholtz contraction. Before scientists understood nuclear fusion, gravitational contraction was once proposed as the source of the sun's energy. It cannot keep the sun shining for billions of years, which became a major problem for 19th century physics. For brown dwarfs, however, gravitational contraction genuinely is an important part of the story. A young brown dwarf contracts and heats internally, while simultaneously radiating energy away. The contraction gradually slows. Something else begins supporting the object against gravity. And this is where quantum mechanics quietly enters our cold little story. As matter becomes extremely compressed, electrons can be forced into conditions where a quantum rule called the Pauli exclusion principle becomes important. Very roughly, electrons cannot all pile into exactly the same quantum state. Compress them more and more, and resistance develops simply because the available low-energy states are already occupied. This produces what is called electron degeneracy pressure. It does not depend on heat in the same way ordinary gas pressure does. That distinction matters enormously. Inside an ordinary young star, gravity squeezes the gas heats. Higher temperature increases pressure. Eventually, if enough mass is present, the core becomes hot enough for sustained hydrogen fusion. The energy from fusion helps maintain the star against gravitational collapse. In a brown dwarf, the object is not massive enough to reach sustained hydrogen-burning conditions before degeneracy becomes increasingly important. The interior becomes compressed enough that electron degeneracy pressure helps resist further contraction. The brown dwarf settles into roughly a Jupiter-sized body without ever turning on the stable fusion engine of a star. This also explains one of the stranger facts we encountered earlier. Adding a great deal of mass to a brown dwarf does not necessarily make it much larger. A brown dwarf containing several dozen Jupiter masses can still have a radius of roughly the same general scale as Jupiter. More mass means stronger gravity. Stronger gravity compresses the material more, so instead of simply becoming proportionally wider, the object becomes denser. Jupiter itself already provides a hint of this strange physics. Saturn is only about 1/3 as massive as Jupiter, yet Jupiter is not 3 times wider. Gas giants and brown dwarfs do not behave like balloons that simply grow in proportion to whatever you put inside them. Gravity makes sure of that. For WISE 0855, this means several Jupiter masses can be packed into something approximately Jupiter-sized, while the object continues cooling at its surface. Once contraction has slowed substantially, however, there is no secret second furnace waiting to rescue it. The interior keeps losing energy. The effective temperature falls, the luminosity falls, the wavelengths at which most radiation escapes shift farther into the infrared, and the brown dwarf becomes progressively more difficult for distant astronomers to detect. This process also changes its atmosphere. Imagine WISE 0855 when it was young. It would have been much warmer than it is today. At high temperatures, many chemical compounds that can exist comfortably now would either have different abundances or would not condense into clouds. As the atmosphere cooled, it crossed one chemical threshold after another. Different materials became stable, some condensed and sank. Other molecules became more prominent in the observable atmosphere. Methane became important at the colder end of the brown dwarf sequence. At still lower temperatures, water itself could begin condensing in sufficiently cool atmospheric regions. The brown dwarf was not simply becoming a dimmer version of the same object. Its visible atmospheric character was changing as it cooled. A warmer L dwarf and an object like WISE 0855 may share broadly similar beginnings, yet their spectra can look dramatically different because temperature has reorganized the chemistry above them. That is one reason a brown dwarf's current appearance contains information about its age, but cannot give us that age directly. Cooling depends on mass. A low-mass object cools differently from a high-mass object. Cooling also depends on atmospheric properties and composition. So when astronomers observe WISE 0855 today, they work backward. They measure its distance. They estimate its total luminosity. They determine how its radiation is distributed across different wavelengths. Then they compare those measurements with models that calculate how substellar objects of different masses should cool over time. Earlier modelling of the Y-dwarf population found that WISE 0855 could plausibly have a mass of roughly 1.5 to 8 Jupiter masses and an age of about 0.3 to 6 billion years, illustrating just how closely mass and age are connected when interpreting such a cold object. That is quite an age range. There is a substantial difference between something 300 million years old and something 6 billion years old. But faint, isolated brown dwarfs do not make age measurements easy. If WISE 0855 orbited a well-understood star, astronomers might estimate the star's age and reasonably assume the two form together. An isolated object offers no such helpful companion. There is no parent star standing beside it saying, "We arrived together." Instead, researchers must infer its history from motion, luminosity, atmospheric properties, and evolutionary calculations. Its faintness therefore tells us two things at once. It tells us that very little energy is currently escaping, and it tells us that some combination of low mass and long cooling time has brought the object to its present state. A particularly low mass WISE 0855 could have cooled rapidly to these temperatures. A more massive WISE 0855 would generally require more time. Both possibilities can reproduce aspects of what we observe. This is why the exact mass remains model dependent. There is another nuclear detail worth mentioning because brown dwarfs occupy such a wide range of masses. Some brown dwarfs are heavy enough to fuse deuterium early in their lives. Deuterium is an isotope of hydrogen containing a proton and a neutron in its nucleus. It can undergo fusion at lower temperatures than ordinary hydrogen. Objects above somewhere around 13 Jupiter masses, with the exact threshold depending on composition and how the calculation is defined, may burn much of their original deuterium for a relatively brief period. This does not turn them into ordinary stars. Deuterium is rare. The supply runs out. Cooling resumes. WISE 0855 is probably below or near the region where substantial deuterium burning would have mattered, given the low masses inferred for it from evolutionary models. So even this temporary source of nuclear energy may have played little or no role in its history. Its story is therefore unusually clean in one sense. Gravity brought it together, collapse heated it. Its interior stored that energy. Then the energy began leaking away, and it has been leaking ever since. There is no nearby star reheating the atmosphere either. That distinguishes WISE 0855 from many giant exoplanets. A hot Jupiter, for example, may orbit extremely close to its star and receive an enormous amount of external radiation. Even an old planet can remain intensely hot on its upper atmosphere because starlight continually pours energy into it. WISE 0855 wanders alone. There is no stellar lamp overhead, no daylight side, no nighttime side, no orbit carrying it through changing amounts of sunlight. Whatever heat reaches its observable atmosphere ultimately comes mainly from within the object itself. That makes WISE 0855 a useful comparison with planets far from their stars, including our own giant planets. Jupiter also emits internal heat. It radiates more energy than it receives from the Sun, partly because it is still cooling and contracting after more than 4.5 billion years. Saturn does too. The basic idea is therefore familiar within our own solar system. Large gaseous bodies remember their formation for a very long time. They carry old heat inside them. WISE 0855 has taken the same general principle much farther from any external source of warmth. The brown dwarf's measured luminosity is extraordinarily small. Recent JW ST/MIRI work combining observations across a broad infrared range derived a bolometric luminosity of only about 5/10 millionths of 1% of the Sun's luminosity, or roughly 10 to the power of minus 7.29 times solar luminosity. The same work found an effective temperature near 285 Kelvin. It is difficult to reconcile that number with the word star. The Sun is constantly flooding Earth with enough energy to warm oceans, drive weather, support photosynthesis, and make the inside of a parked car unpleasantly ambitious. WISE 0855's total output is millions of times weaker. Yet the important thing is not simply that it is dim, it is still radiating. After perhaps billions of years, energy left from formation and contraction continues escaping into space. The object has not reached absolute zero. It never will in any practical sense. Cooling becomes slower as the temperature difference between an object and its surroundings becomes smaller, and space itself is not literally at absolute zero. The universe contains the cosmic microwave background and other radiation fields. For WISE 0855, though, the surrounding interstellar environment is still vastly colder than the brown dwarf. So outward heat flow continues. Very gradually, WISE 0855 will become fainter. Its atmosphere will cool further. Chemical transitions will continue. In the distant future, it may reach temperatures lower than any brown dwarf we have characterized today. This raises an interesting consequence for the whole population. The Milky Way has existed for more than 13 billion years. Brown dwarfs that formed early in the galaxy's history have therefore had an enormous amount of time to cool. The oldest low-mass examples could now be extremely cold and extraordinarily difficult to detect. WISE 0855 may not be special because nature rarely makes objects like it. It may be special because we happen to have one close enough to see. A much colder object at 100 light-years could evade present surveys. A comparable object on the other side of the galaxy would disappear into practical invisibility. So the record of coldest known brown dwarf is partly a record of our observational limits. There could be darker ones, older ones, lower mass ones, objects that began through the same general gravitational processes as stars but have spent most of cosmic history fading. It is almost the opposite of how we usually imagine stellar evolution. Massive stars become more dramatic with age. They swell. Their interiors build heavier elements. Some end in enormous supernova explosions, briefly becoming bright enough to rival entire galaxies. A low-mass brown dwarf does nothing of the sort. Its aging process is remarkably undramatic. No red giant phase, no supernova, no spectacular final explosion. It simply becomes colder and colder. The chemistry changes. The light weakens. The peak of its radiation moves into longer wavelengths. Eventually, an object that may once have glowed at temperatures of thousands of Kelvin can reach the temperature range of a cold planetary atmosphere. If the universe allowed us to watch the entire process at high speed, we would see the brown dwarf gradually disappearing from visible light, then changing through infrared colours as molecules and clouds reorganized. At some point it would resemble an L dwarf, later a T dwarf, later still a Y dwarf. The transitions would not be perfectly neat because clouds, composition, surface gravity, and atmospheric mixing all complicate matters. Nature prefers a gradient whenever astronomers would appreciate a filing cabinet. WISE 0855 represents what happens when that cooling is allowed to proceed unusually far. Its low effective temperature does not mean it somehow avoided being hot. Quite the opposite. It tells us that it once possessed considerably more thermal energy and has successfully spent a very long time getting rid of it. Every infrared photon arriving in our telescopes is part of that process. it left a deeper, warmer region. It passed through atmospheric layers containing molecules capable of absorbing particular wavelengths. Perhaps it was absorbed and re-emitted more than once. Eventually it escaped. Then it travelled a little more than 7 years through interstellar space before reaching a telescope near Earth. Astronomers collect enough of those photons and reconstruct the temperature and chemistry of a body we cannot see directly. And because different wavelengths escape from different depths, a spectrum can reveal something even more useful than a single temperature. It can probe layers. That matters because an atmosphere is not all one temperature. Move downward and conditions change. Pressure rises, temperature rises, chemical abundances shift. Clouds may appear at particular levels. Convection may transport gases upward, faster than chemical reactions can adjust them. The 285 Kelvin brown dwarf is therefore not a ball uniformly sitting at 285 Kelvin. It is a complicated atmospheric column resting on top of a much hotter interior. The effective temperature is a convenient description of the object's total energy loss, not a complete weather report. This distinction becomes especially important once water enters the picture. At temperatures as low as those around WIC 0855, water can condense from vapour in parts of the atmosphere. Recent JWST observations have found evidence that gaseous water becomes depleted higher in the atmosphere in a way consistent with condensation. Researchers have not, however, found an unambiguous spectral signature of the water ice clouds themselves in those data. That may sound like a small technical distinction. It is actually exactly the sort of detail astronomers hoped WISE 0855 would allow them to investigate. An atmosphere this cold gives us access to cloud physics that warmer brown dwarfs cannot provide. As the object cooled through hundreds of degrees over immense periods, it eventually crossed into a regime where ordinary water began behaving as a condensable substance, rather than remaining only as hot vapour. The same gradual loss of internal heat that made WISE 0855 almost impossible to discover has therefore made it scientifically valuable. It has cooled into the territory of planets, and once a brown dwarf reaches those temperatures, its atmosphere stops looking like the atmosphere of a faint star and starts presenting a much more familiar collection of planetary ingredients: water, methane, ammonia, carbon-bearing molecules, cloud formation, vertical circulation, weather. The cold itself becomes a laboratory. Once an object becomes as cold as WISE 0855-0714, knowing that it exists is only the beginning of the problem. The next difficulty is getting enough light from it to learn anything useful, and WISE 0855 is not generous with light. At visible wavelengths it is effectively absent. Point an ordinary optical telescope toward its position, and you do not get a tiny brown star waiting politely in the middle of the image. You get a field of background sources and, where WISE 0855 ought to be, almost nothing useful at all. This is not because the object is especially small. Its radius is roughly comparable to Jupiter's, nor is it because it is on the far side of the Milky Way. It is only a little more than 7 light-years away. The problem is temperature. At only a few hundred Kelvin, WISE 0855 emits most of its energy in the infrared, and even there its glow is remarkably weak. NASA described it at discovery as an object whose thermal radiation was feeble, even though infrared telescopes could detect it. Later attempts to study it showed just how extreme that faintness really was. To understand why, think about the difference between a light bulb and a warm radiator. A traditional incandescent bulb contains a filament heated until it becomes hot enough to glow visibly. Your eyes can see the light because the filament reaches temperatures of thousands of degrees. A radiator in a warm room is also releasing electromagnetic radiation. You simply cannot see most of it. Its temperature is too low for significant visible light, so much of its thermal emission appears in the infrared. WISE 0855 is much closer to the second case, except the radiator is roughly the size of Jupiter, floating through interstellar space, and there is no convenient wall behind it. The basic physics comes from thermal radiation. Objects at different temperatures tend to release their energy most strongly at different wavelengths. Make something hotter, and its radiation shifts toward shorter wavelengths. Cool it down, and the peak shifts toward longer ones. The sun is hot enough that a great deal of its radiation falls in the visible range. A person emits strongly in infrared. A cold brown dwarf like WISO-855 pushes much of its radiation farther into the infrared still. This means that if astronomers want to study the object, choosing the correct wavelength is not a minor technical detail. It determines whether the object is visible at all. WISE was built for exactly this kind of search. Instead of observing only the light human eyes can detect, it mapped the sky in infrared bands. Because the mission surveyed the whole sky repeatedly, it could find cold sources and also compare their positions over time. WISO-855 first became noticeable partly because its faint infrared point moved rapidly between observations. But detecting a moving point and obtaining a useful spectrum are very different tasks. A photograph can tell you that something is there. A spectrum can tell you what is in its atmosphere. To obtain one, astronomers take the incoming light and separate it into wavelengths, rather like spreading white light through a prism. The trouble is that dividing faint light into many wavelength bins makes every individual part even fainter. Imagine trying to determine the ingredients in a distant candle flame. First, make the candle almost invisible, then spread its tiny amount of light across hundreds or thousands of separate measurements. Now try to distinguish real chemical features from detector noise, background radiation, Earth's atmosphere, and everything else the universe has thoughtfully placed between you and the candle. That begins to resemble the problem. The traditional approach for studying many brown dwarfs is near-infrared spectroscopy. Warmer brown dwarfs can be reasonably bright in certain near-infrared regions, so astronomers can collect enough photons to identify molecules and compare their spectra with atmospheric models. WISE. 855 is too cold for that method to work easily. Its near-infrared emission is extraordinarily weak. Early observations sometimes produced only upper limits. That means the telescope did not obtain a secure detection, and could say only that the object must be fainter than a certain brightness. Normally, not seeing something sounds disappointing. In astronomy, a non-detection can still be useful. If a model predicts that WISO-855 should be bright at a particular wavelength, and the telescope sees nothing, the model has a problem. An upper limit can eliminate possibilities. It can constrain temperature. It can test cloud models. It can tell astronomers that the object's atmosphere is blocking more radiation at that wavelength than expected. So even darkness contains information, provided you measure the darkness carefully enough. Researchers eventually carried out very deep imaging of WISO-855 with facilities including Gemini, the Very Large Telescope, the Hubble Space Telescope, and Spitzer. In one study, 6 optical and near-infrared bands were targeted. 5 produced detections, one of them only marginal, and the results showed that no single atmospheric model could reproduce all of the object's measured colours particularly well. That phrase, deep imaging, sounds rather calm. What it really means is that astronomers collect light for a long time because there isn't much of it. A camera on your phone can take a photograph in a fraction of a second. Because daylight provides huge numbers of photons, astronomy frequently works in the opposite regime. Leave the detector exposed, collect photons, keep collecting. Correct for the instrument, correct for the sky. Combine exposures, remove cosmic ray hits, subtract backgrounds. Check whether the tiny remaining signal is actually the object rather than some enthusiastic piece of noise pretending to be important. For WISO-855, patience became part of the instrument. The Earth's atmosphere made matters worse. Infrared radiation does not travel through our atmosphere equally well at every wavelength. Water vapour, carbon dioxide, methane, and other gases absorb large portions of the infrared spectrum. This is excellent for keeping Earth habitable. It is less convenient when you're trying to measure water and methane in an object 7 light-years away. Our atmosphere contains many of the same kinds of molecules astronomers would like to detect elsewhere, so the signal arriving from WISE 0855 passes through a layer of terrestrial chemistry that can partially absorb it before it reaches a ground-based telescope. There are, fortunately, atmospheric windows where infrared radiation can pass through more effectively. One especially important region for WISE 0855 lies near 5 microns. At these wavelengths, radiation from warmer, deeper parts of the brown dwarf's atmosphere can escape through a relatively transparent spectral window. That made the object brighter there than it is across much of the near-infrared. Not bright, just less impossible. In 2016, astronomers used the Gemini North Telescope in Hawaii to obtain the first spectrum of WISE 0855 over roughly 4.5 to 5.2 microns. They accumulated observations across 13 nights, totaling about 14 hours of integration. The object was about 5 times fainter than any source previously studied with ground-based spectroscopy at that wavelength. 14 hours for one narrow slice of infrared light. That gives you some sense of the problem. If you have ever tried to photograph something in a dark room and watch the camera struggle, imagine extending that difficulty to a target that cannot be made brighter, cannot be moved closer, and will remain approximately 7 light-years away no matter how politely you ask. Large telescopes help because they collect more light. Gemini North has an 8.1 meter primary mirror. A larger collecting area means more photons reach the instruments during a given amount of time, but simply building a large mirror does not solve everything. At around 5 microns, the telescope itself and the atmosphere around it produce infrared radiation. Anything warm glows in infrared. That includes the sky. That includes the telescope structure. That includes parts of the instrument. Astronomers trying to detect a faint thermal source are therefore working against a background produced by their own environment. It is a little like trying to hear someone whisper while the room itself is humming. The solution involves careful calibration and background subtraction. Astronomers repeatedly measure the target and nearby sky, allowing them to estimate the unwanted infrared background and subtract it from the data. Do this poorly, and the background overwhelms the brown dwarf. Do it carefully enough, and the faint spectrum emerges. The Gemini result was remarkable because it showed that WISE 0855 spectrum around 5 microns contained strong signatures associated with water vapour and had an overall shape strikingly similar in some respects to Jupiter's spectrum in the same wavelength region. That comparison with Jupiter was not accidental. Planetary scientists had long studied Jupiter's deep thermal emission through a similar 5-micron window. At those wavelengths, some radiation can emerge from relatively deep, warm atmospheric layers rather than being completely absorbed higher up. UICE 0855 offered an extrasolar version of the same basic experiment. Only instead of pointing toward Jupiter, a few astronomical units away, astronomers were collecting photons from a brown dwarf more than 7 light-years from Earth. The similarity immediately made WISE 0855 feel less like a very faint star, and more like a distant giant planetary atmosphere. Still, that first spectrum had limits. It covered only a narrow region. A spectrum is most useful when you can observe a broad range of wavelengths, because different molecules leave fingerprints in different places. Water absorbs strongly in some regions, methane in others, carbon monoxide elsewhere. Some wavelengths probe high atmospheric layers, others allow us to see deeper. If you observe only a small window, you're trying to understand an entire building while looking through one letterbox. This is where space telescopes become especially valuable. Above Earth's atmosphere, the terrestrial absorption problem disappears. The background can also be far lower if the telescope itself is kept cold. NASA's Spitzer Space Telescope was particularly useful because it observed in infrared from space and could repeatedly measure WISE 0855. Spitzer data contributed to the object's distance measurement, temperature estimates, photometry, and later monitoring of brightness changes. Those brightness changes revealed another important point. WISE's 0855 was not perfectly constant. Spitzer monitored it at 3.6 and 4.5 microns during 2 observing periods lasting about 23 hours each. Researchers detected brightness variations of a few percent. The patterns change between the 2 observing epochs, with more regular behavior in one and more irregular behavior in the other. A faint object becoming a few percent fainter and brighter may not sound dramatic, but when an unresolved brown dwarf varies as it rotates, astronomers can infer that its atmosphere is not uniform. One hemisphere may not look exactly like another. There could be differences in cloud coverage, temperature, chemical abundance, or atmospheric structure. You cannot photograph individual cloud systems. WISE 0855 is much too distant and much too small on the sky for that. Instead, you watch the total light. As different regions rotate into view, the brightness changes. This is similar to watching a rotating ball that has one dark patch on it. Even if the ball is too far away for you to resolve the patch itself, the total brightness will fall slightly whenever the darker side faces you. Astronomers call this kind of work time series photometry. In the case of WISE 0855, it offered a way to study possible weather without ever seeing a single cloud. And then came a telescope designed for exactly the wavelengths, where objects like this become much easier to investigate. The James Webb Space Telescope did not make WISE 0855 bright. Nothing can do that. What JWST changed was our ability to collect and separate its faint infrared radiation. Its large segmented mirror provides a collecting area far beyond earlier infrared space telescopes, while its instruments cover near and mid-infrared wavelengths with high sensitivity. Most importantly, JWST operates above Earth's atmosphere and keeps much of the observatory extremely cold. For an object whose entire scientific value lies in tiny amounts of infrared radiation, that combination is transformative. Using JWST's near-infrared spectrograph, or NIR-SPEC, astronomers obtained spectroscopy of WISE 0855 from roughly 1 to 5 microns. Compared with earlier measurements, the new observations dramatically improved wavelength coverage, spectral resolution, and signal-to-noise ratio. Signal-to-noise is one of those phrases astronomers use constantly, because it determines whether the tiny wiggle in a graph is telling you something about another world, or something about your detector having a difficult afternoon. The signal is what you want. The noise is everything that obscures it. If the signal is strong compared with the noise, spectral features become clear. If the noise is comparable to the signal, interpretation becomes uncertain. WISE 0855 spent years living close to the second situation. JWST moved much more of its spectrum toward the first. Suddenly, researchers could see molecular absorption across a much broader wavelength range. They identified carbon monoxide in the atmosphere, supporting the idea that gases are being mixed vertically between different atmospheric levels. They could also test earlier interpretations of water clouds, and found that some portions of the spectrum could be reproduced surprisingly well by cloudless models, making the cloud question more complicated than it had initially appeared. This is an important part of what better observations do. They do not always confirm the simpler story. Sometimes they remove uncertainty. Sometimes they reveal that the uncertainty was larger than anyone realized. The first ground-based spectrum had been interpreted as strong evidence for water clouds or water ice. Later work noted that the evidence was not yet completely secure. JWST then produced spectra detailed enough to show that at least some features previously associated with clouds could also be explained without obvious cloud signatures. That does not mean earlier observations were useless or wrong. They were working at the limit of what the available instruments could measure. As sensitivity improves, models become more demanding. A theory that fits 5 photometric measurements may struggle when confronted with 500 spectral points. The object hasn't changed its mind. We have simply started asking it more precise questions. Even now, one of the strange aspects of WISE 0855 is that almost everything we know about it comes from a source that would look thoroughly unimpressive in an ordinary image. No telescope has produced a close-up view of cloud bands wrapping around a brown sphere. No photograph shows storms, vortices, lightning, or a recognizable atmospheric surface. At more than 7 light-years away, its angular size is far too small for current telescopes to resolve its disk. When we show WISE 0855 in illustrations, the detailed appearance is imagined from atmospheric models and comparisons with planets such as Jupiter. The real observational data are much less cinematic. Points of light, brightness measurements, spectra, graphs, positions, changes over time. From those, researchers reconstruct an object. Temperature comes from the amount and distribution of radiation. Distance comes from parallax. Motion comes from astrometry. Atmospheric molecules come from spectral absorption. Possible weather comes from variability. Mass comes indirectly from evolutionary models because there is no orbiting companion conveniently revealing the gravitational pull. This is one of astronomy's most impressive habits. It turns things we cannot see directly into things we can understand quantitatively. Suppose a particular wavelength contains less radiation than neighbouring wavelengths. That may indicate a molecule absorbing there. Suppose the same absorption pattern appears at several related wavelengths. Confidence increases. Suppose atmospheric models containing water reproduce the pattern, and models without water do not. Now water becomes a strong inference. Suppose carbon monoxide appears in quantities that should not persist in the observable layers under simple chemical equilibrium. That suggests material has been transported upward from deeper, hotter regions. Suddenly, a tiny dip in infrared brightness has become evidence for atmospheric circulation on an object 7 light-years away. There is nothing magical about it. There is a great deal of mathematics, which is sometimes the closest astronomy gets. The extreme faintness of WISE 0855 also tells us something uncomfortable about how incomplete our census of the nearby universe may still be. WISE found this object because it is close. If an identical brown dwarf were much farther away, the amount of light reaching us would fall rapidly with distance. Double the distance and the same radiation spreads over 4 times the area. Move the object 10 times farther away, and it appears 100 times fainter. WISE 0855 is already difficult at 7 light-years. Is already. There could be many similar objects elsewhere in the Milky Way that our current surveys simply cannot characterize, and some may be too faint even to detect easily. This is why the phrase "coldest known brown dwarf" needs one quiet word of caution. Known. Astronomers are not claiming that no colder brown dwarf exists anywhere in the universe. They are saying that WISE 0855 remains the coldest one we have identified and studied well enough to establish its nature. A colder object could be drifting through the galaxy tonight. Several could be. Thousands could be. If they are distant enough, their thermal glow may never reach our detectors in sufficient quantities for us to notice them with present technology. Finding the cold population is partly a search for objects approaching invisibility. NASA's latest citizen science projects have continued using WISE and NEO-WISE images to search for faint nearby brown dwarfs by looking for motion across repeated observations. The method is almost charmingly straightforward. Instead of expecting a cold object to announce itself through brightness, watch for a faint point that changes position. Computers can help enormously with this, so can human eyes. When images from different years are combined into animations, nearby moving objects can stand out against distant stars and galaxies. A tiny dot shifts. That movement is enough to say, this one deserves another look. It is essentially the same clue that first drew attention to WISE 0855, now applied across enormous survey archives in the hope of finding more members of the same hidden population. The objects being sought are not necessarily spectacular. That is exactly the point. Astronomy spent much of its history being naturally biased toward things that shine. Bright stars, explosions, galaxies, glowing nebulae. Cold brown dwarfs require the opposite instinct. Look for what barely shines. Use wavelengths human eyes cannot detect. Compare observations separated by months or years. Take non-detection seriously. Collect photons for hours. Build colder instruments. Put telescopes above the atmosphere. Then take a source that appears as a few weak measurements and ask what kind of atmosphere could produce them. WISE 0855 may be one of the best examples of how far that approach can go. The first observations established a faint moving infrared source. Spitzer helped turn that source into a nearby object with a measured distance. Deep imaging began tracing its spectral energy distribution. Gemini spent 14 hours gathering enough light for a narrow spectrum. Spitzer watched its brightness change with time. JWST expanded the spectrum across a much broader range and exposed chemical features that had previously been hidden in the noise. Each improvement has been less about making WISE 0855 easier and more about making our instruments better at dealing with difficulty. The brown dwarf has continued doing what it has probably done for billions of years, cooling, rotating, circulating gases, releasing a tiny amount of internal heat. It did not brighten when WISE launched. It did not arrange its molecules more conveniently when Gemini observed it. It did not increase its contrast for JWST. We simply became better at listening to the very weak signal it had been producing all along. And that weak signal is now enough to begin asking questions that would have seemed unrealistic when WISE 0855 was first identified. How quickly does its atmosphere circulate? Which molecules dominate at different depths? How much carbon monoxide is being carried upward? Does water condense into clouds, and if so, where? Are different parts of the atmosphere warmer than others? What happens to cloud formation at temperatures close to those of giant planets? How similar is this isolated brown dwarf to Jupiter once you remove the Sun from the comparison? The faint infrared radiation reaching us from WISE 0855-0714 has already told astronomers that this object is cold, nearby, and remarkably dim. But once that radiation is separated into a spectrum, it begins to reveal something much more detailed. It gives us a way to investigate the atmosphere itself. That atmosphere is not a thin shell sitting above a solid surface. WISE 0855 is a gaseous object, and as far as we know, there is no ordinary ground beneath its clouds where you could land, place a flag, and immediately regret not bringing a heavier coat. As you move downward, gas simply becomes denser, hotter, and more strongly compressed. Eventually, the distinction between atmosphere and interior becomes less obvious. The upper layers are dominated by hydrogen and helium, the same two elements that make up most of Jupiter and most stars. Hydrogen is especially abundant, usually in molecular form, with two hydrogen atoms joined together as H2. Helium makes up much of the remainder. Those ingredients sound simple. The atmosphere they create is not. Mixed among the hydrogen and helium are smaller quantities of molecules that have an enormous effect on the spectrum. Water vapour absorbs infrared radiation across broad wavelength regions. Methane produces its own distinctive features. Ammonia becomes important in very cold atmospheres. Carbon monoxide appears where basic equilibrium chemistry might not expect so much of it. Other compounds exist in trace quantities, and even rare versions of familiar molecules can now be measured with sufficiently precise observations. This is where WISE 0855 begins looking less like a tiny star and more like a giant planet. A normal star is so hot that molecules cannot survive through most of its visible atmosphere. At thousands of degrees, atoms and ions dominate the discussion. WISE 0855 is cold enough for molecular chemistry to take over. Instead of asking which atoms are ionized, researchers can ask how much methane is present, where water condenses, whether ammonia remains gaseous, and how quickly material is being transported between atmospheric layers. Those are questions that would sound perfectly ordinary in a conversation about Jupiter. They sound slightly more surprising when the object formed through a process associated with stars. The temperature we usually attach to WISE 0855, somewhere in the neighbourhood of roughly 260 to 285 Kelvin, depending on how it is derived, does not mean every part of its atmosphere sits at that temperature. An atmosphere has structure. Earth does too. The temperature outside your window tells you very little about the temperature several kilometres above your head, and absolutely nothing about conditions hundreds of kilometres below your feet. WISE 0855 takes that idea much further. At high altitudes, pressures are low and temperatures are comparatively cool. Descend deeper, and gravity compresses the gas. Pressure rises, temperature rises as well. Eventually, the layers become hot enough that molecules behave very differently from the way they do near the regions we observe directly. So when astronomers study WISE 0855, different infrared wavelengths can effectively allow them to peer to different depths. This happens because gases are not equally transparent at every wavelength. Imagine looking into a swimming pool through several different pairs of glasses. One pair is nearly clear, allowing you to see far down into the water. Another is dark enough that you see only the surface. Molecules in an atmosphere create something similar. At wavelengths where water or methane absorbs strongly, radiation coming from deep layers is blocked. The light we receive at those wavelengths therefore tends to come from higher in the atmosphere. At wavelengths where the gases absorb less efficiently, radiation can escape from deeper, hotter regions. The result is that a spectrum contains information not only about which molecules are present, but also about the atmosphere's vertical structure. That is extremely useful when your target is a point of light too distant to resolve. We cannot photograph the individual atmospheric layers of WISE 0855. We can still investigate them indirectly. Around 5 microns, for example, the atmosphere contains a region of relatively low opacity, where thermal radiation can escape from deeper levels. That is one reason early ground-based spectroscopy focused on this part of the infrared. At other wavelengths, absorption by water, methane and ammonia becomes stronger, shifting the level from which the observed radiation emerges. JWST has now allowed researchers to collect spectra across much larger wavelength ranges, effectively giving them more vertical information than earlier observations could provide. One of the strongest molecular signatures is water. Water vapour had already been detected in observations before JWST, and the newer spectra now trace water over a much broader range. This does not mean there is anything resembling an ocean floating inside WISE 0855. The water is mixed through a hydrogen-rich atmosphere under pressures and temperatures very different from those at Earth's surface. Still, chemically, it is the same basic molecule, H2O. That familiarity can make the atmosphere feel strangely approachable. 7 light-years away, in an object with several times Jupiter's mass, water molecules are absorbing infrared photons at exactly the wavelengths predicted by laboratory physics on Earth. The molecule has no idea where it is. Its energy levels work the same way. That consistency is what allows spectroscopy to function. Methane is another major ingredient. Methane, CH4, contains 1 carbon atom bonded to 4 hydrogen atoms. It is common in the atmospheres of the outer planets of our solar system, including Jupiter, Saturn, Uranus and Neptune. It is also expected to become increasingly important as brown dwarfs cool. At high temperatures, carbon chemistry favours different molecules. At lower temperatures, methane becomes more stable. That transition is so important that strong methane absorption is one of the defining characteristics of T-type brown dwarfs, and methane remains a major atmospheric molecule in the even colder white dwarfs. WISE 0855 is certainly cold enough. Its spectrum shows strong methane absorption, particularly around wavelengths where methane's vibrational modes interact with infrared radiation. In a spectrum, those interactions appear as sections where less light escapes. You can think of the molecule as removing certain colours of infrared light from the outgoing radiation. not randomly. Methane always prefers particular wavelengths determined by quantum mechanics. Water prefers its own collection. Ammonia has another. Carbon monoxide has another. Overlay all of these together, add pressure, temperature, clouds, collisions, and a hydrogen-dominated background, and you obtain the complicated spectrum astronomers actually measure. Ammonia is especially interesting at these temperatures. NH3 is familiar on Earth mostly as a cleaning chemical, with a smell that encourages you to open a window immediately. In a cold brown dwarf, it is simply another atmospheric molecule. As temperatures decline, ammonia becomes increasingly favoured compared with molecular nitrogen under chemical equilibrium. JWST's mid-infrared observations contain strong ammonia features and have even allowed researchers to detect a rare isotopic form containing nitrogen-15. Normally, ammonia contains the more common isotope nitrogen-14. Replace that nitrogen atom with the rarer nitrogen-15 isotope, and you get a molecule that is chemically almost identical, but produces subtly shifted spectral features. The fact that astronomers can detect something this specific in WISE 0855 is a useful measure of how far observations have improved. A little over a decade ago, the object was a faint moving source in survey data. Now astronomers can examine the isotopic composition of individual molecules in its atmosphere. That is a rather substantial promotion. The ratio between different isotopes can eventually provide clues about formation and chemical history. Different environments can process isotopes differently, so comparing ratios among brown dwarfs, giant planets, comets, and other objects may help researchers understand where material originated and how it evolved. The measurements are still difficult, but WISE 0855 is becoming a test case for exactly this kind of work. Researchers have also detected deuterated methane, CH3D. Deuterium is a heavier isotope of hydrogen. Ordinary hydrogen contains one proton in its nucleus. Deuterium contains one proton and one neutron. Replace one ordinary hydrogen atom in methane with deuterium, and CH4 becomes CH3D. Again, the difference is tiny. Again, spectroscopy can detect it because the additional mass shifts the molecule's vibration and rotation slightly. Recent JWST work has used this feature to estimate the ratio of deuterium to ordinary hydrogen in WIC 0855. That ratio matters because deuterium can be destroyed in sufficiently massive brown dwarfs during their early lives. Objects above the deuterium burning threshold can reach core conditions hot enough to consume a significant fraction of their original deuterium. Lower mass objects preserve it. Finding a roughly protosolar deuterium abundance in WIC 0855 is therefore consistent with an object that did not undergo substantial deuterium burning, supporting the view that its mass lies in the very low brown dwarf or planetary mass regime. That is an impressive amount of information to extract from a molecule containing 5 atoms. The atmosphere contains another molecule that tells us something entirely different. Carbon monoxide. CO is very simple. One carbon atom, one oxygen atom. At first glance, finding carbon monoxide does not sound particularly exciting. We have carbon monoxide on Earth. You would prefer not to have much of it in your kitchen, but cosmically speaking, it is not an exotic molecule. The interesting part is where it appears. In the cool observable atmosphere of WIC 0855, basic chemical equilibrium calculations would tend to place much of the carbon into methane rather than carbon monoxide. Deeper inside, where temperatures are higher, carbon monoxide becomes much more favourable. Yet CO is visible in the spectrum. That means the atmosphere is not sitting quietly in perfect chemical equilibrium. Gas is moving. Material from deeper, hotter levels is being carried upward into cooler regions. If that transport happens faster than the chemical reactions converting carbon monoxide into methane, some CO survives long enough to reach levels where we can detect it. Astronomers call this disequilibrium chemistry. The name sounds dramatic, but the idea is straightforward. Imagine moving a tray of ice cubes from a freezer into a warm kitchen. Given enough time, the ice reaches equilibrium with the room and melts. carry it back into the freezer before that happens, and it retains a state that no longer matches its surroundings. Atmospheric chemistry can behave in a similar way. Gas moves between regions faster than some chemical reactions can adjust. Its composition therefore contains information about where it has been. In WISE 0855, carbon monoxide acts as a tracer of vertical mixing. The atmosphere is circulating material between depths. That should immediately remove any picture of this object as a completely static frozen ball. Its exterior is extremely cold by brown dwarf standards, but underneath that cold exterior, heat continues escaping from the interior. Heat produces temperature differences. Temperature differences help drive motion. Gas rises. Other gas sinks. Convective regions occur deeper down, while radiative transport becomes more important elsewhere. The details depend on pressure and temperature, but the broad point is simple. WISE 0855 has atmospheric dynamics. It has circulation. It has chemistry that is being disturbed by that circulation, and all of this is happening without sunlight. Earth's weather is powered largely by energy from the sun. Different parts of the planet receive different amounts of solar heating. Warm air rises, cold air sinks. Water evaporates, condenses, and falls. Rotation organizes large-scale circulation. WISE 0855 has no nearby star providing that energy. Its atmosphere is primarily powered from below. Heat left over from formation and contraction slowly emerges from the interior. That internal heat provides the energy flowing outward through the atmosphere. Jupiter works partly this way too. It receives sunlight, but it also radiates substantial internal energy. WISE 0855 gives us a much cleaner version of that situation, because stellar heating is essentially absent. That makes its pressure-temperature profile especially interesting. If researchers can measure how temperature changes with pressure, they can test models of how cold self-luminous atmospheres transport energy. Some levels may be convective, with moving gas carrying heat efficiently upward. Higher regions can become stable against convection, leaving radiation to do more of the work. Molecular absorption determines how easily that radiation escapes. Change the abundance of methane or water, and you change the atmosphere's opacity. Change the opacity and you can alter the temperature structure. Add clouds and the problem becomes more complicated again. This interaction between chemistry and temperature means atmospheric modelling is not simply a matter of choosing a few molecules and calculating a spectrum. Everything affects everything else. The temperature determines which molecules are stable. The molecules determine how radiation moves. Radiation influences the temperature. Vertical mixing changes the chemical abundances. Clouds can block radiation and alter heating. Gravity sets how rapidly pressure changes with altitude. Metallicity changes the overall supply of elements heavier than hydrogen and helium. A model has to keep these relationships physically consistent enough to reproduce the observed spectrum. Sometimes it does. Sometimes WISE 0855 reminds everyone that nature is under no obligation to fit the first model tried. The earliest models of very cold brown dwarfs predicted various spectral features that did not perfectly match observations. Methane has been particularly troublesome across the white dwarf population. Cloud models have changed. Chemical reaction networks have improved. Opacity databases have improved as laboratory measurements and theoretical calculations became more complete. JWST has now provided spectra precise enough that shortcomings in atmospheric models can no longer hide easily inside large error bars. That is good news. A model failing is useful when the data are trustworthy. It tells you that some physical assumption needs attention. One particularly curious example involves phosphine, pH 3. Phosphine is a molecule containing phosphorus and hydrogen. In Jupiter and Saturn, it is observed because material is mixed upward from deeper, hotter atmospheric regions, where phosphine can form more readily. For that reason, researchers expected that a cold white dwarf showing strong vertical mixing might also display phosphine. Early JWST analysis of WISE 0855 did not find the amount that some models predicted. Later, more detailed retrieval work reported phosphine at only about 1 part per billion, so it appears to be present but at an extremely low abundance. This is precisely the sort of puzzle that makes an atmosphere scientifically useful. Carbon monoxide says vertical mixing is occurring. Phosphine says our understanding of how phosphorus chemistry responds to that mixing is incomplete. The atmosphere is effectively agreeing with the model on one page and disagreeing on the next, which is inconvenient if you wrote the model, but rather helpful if your goal is to learn new physics. Gravity also shapes everything occurring there. A brown dwarf has no solid surface where we can measure gravity directly by dropping something, and dropping equipment into WICEO 855 would probably have a disappointing effect on the equipment. Instead, astronomers infer surface gravity through atmospheric spectra and evolutionary models. Greater gravity compresses the atmosphere more strongly. For a given temperature, pressure changes more rapidly with altitude. Spectral lines broaden differently. Cloud structures shift. The combination of radius, mass, and gravity therefore affects the spectrum in subtle ways. WISE. 855's exact mass is uncertain because it has no known companion whose orbit could provide a direct dynamical measurement. That leaves atmospheric retrievals and evolutionary calculations doing much of the work. A retrieval is essentially an organized attempt to reverse the problem. Normally, you begin with an atmospheric model and calculate what spectrum it should produce. A retrieval starts with the observed spectrum and asks which combinations of temperature, gravity, molecular abundances, radius, clouds, and other parameters are most consistent with it. There may be millions of possible combinations. Computer algorithms explore them and determine which regions of parameter space fit the data best. The answer does not arrive as a single perfect atmosphere. It arrives as probabilities. Some temperatures are more likely than others. Some water abundances fit better. Some gravity values can be excluded. Some combinations produce spectra that clearly disagree with JWST. Slowly, the range narrows. For WISE 0855, combining near and mid-infrared observations has greatly expanded the portion of the atmosphere that can be tested. JWST's NISAR spec measurements cover important near-infrared molecular features, while MIRI extends into the mid-infrared, where cooler atmospheric layers and molecules such as ammonia become particularly important. Together, observations have produced a spectrum stretching from less than 1 micron out beyond 20 microns. That covers a substantial fraction of the object's emitted energy and gives researchers much stronger constraints on its total luminosity and atmospheric composition. The MIRI observations produced another important result involving water. Researchers found that the abundance of water vapor decreases in the upper atmosphere in a way expected when water begins to condense. Think of air on Earth cooling until it can no longer hold the same amount of water vapor. Water leaves the gas phase and forms liquid droplets or ice. On WISE 0855, the temperatures are low enough that water is expected to condense into ice particles. The measured depletion of gaseous water with altitude is consistent with that process occurring. Interestingly, the spectra have not yet produced an unambiguous direct signature of the water ice cloud particles themselves. That distinction is worth keeping. The water vapor appears to be condensing. Atmospheric models strongly expect water ice clouds under appropriate conditions. Earlier observations offered evidence for them, yet the newest spectra can still be matched without requiring a clear, easily identifiable cloud signature. So the most accurate picture is not JWST photographed water clouds. It did not. The better statement is that JWST is probing the atmospheric levels where water condenses, and the changing abundance of water vapor provides strong evidence for that condensation, while the exact spectral appearance and distribution of the resulting clouds remain active areas of study. This is where WISE 0855 becomes especially valuable as a comparison with Jupiter. Jupiter contains water clouds too, but they form relatively deep beneath higher cloud decks that include ammonia. That makes direct study difficult. WISE 0855 is warm enough that ammonia is not expected to form the same dominant upper cloud layer under the relevant conditions, while being cool enough for water to condense. That potentially exposes water cloud physics more directly. It is an unusual atmospheric arrangement that happens to be sitting only a little over 7 light-years from us. The comparison should not be pushed too far. WISE 0855 is not simply Jupiter without the Sun. Its mass may be several times greater. Its gravity can be stronger. Its elemental composition may differ. Its formation history is probably different. Its atmospheric circulation does not receive the same external solar heating. But the similarities in temperature and molecular chemistry are close enough that each object helps us understand the other. Models tested against Jupiter can be applied to WISE 0855. Models built for cold brown dwarfs can eventually help interpret giant exoplanets. That connection matters because directly studying temperate giant exoplanets is exceptionally difficult. If a cold Jupiter-sized planet orbits another star, the star overwhelms it with light. WISE 0855 has kindly removed the star. We can observe its own thermal spectrum without having to separate it from a nearby stellar source. That turns an obscure brown dwarf into a useful practice target for future planetary astronomy. The techniques being developed now, retrieving water abundances, measuring methane, tracing vertical mixing with carbon monoxide, searching for cloud signatures, examining isotopes, are exactly the kinds of techniques astronomers hope to apply to increasingly cold exoplanets as telescopes improve. YCO 855 is therefore giving us an atmospheric laboratory under planetary temperatures before we can routinely obtain comparable spectra from actual Jupiter analogues around other stars. And there is still a great deal we cannot see. We do not know exactly what its cloud patterns look like. We do not know whether it has bands resembling Jupiter's belts and zones. We do not know how large its storms might become. We do not have a detailed map of temperature across its atmosphere. We cannot watch individual clouds form and disappear. Instead, we receive the combined light from the whole unresolved disk. If one region becomes brighter while another becomes darker, all we see is a slight change in total infrared brightness. But those changes are enough to suggest that the atmosphere is not uniform. As WISE 0855 rotates, different regions come into view. Changes in clouds, temperature, and chemistry can subtly alter the amount of radiation escaping. By monitoring those variations over many hours, astronomers can begin separating one possibility from another. That takes us beyond asking what the atmosphere contains. It begins asking what the atmosphere is actually doing. Treating the atmosphere as weather rather than as a static collection of gases changes the picture of WISEO 855-0714 considerably. A temperature of only a few hundred Kelvin can make the object sound inactive, as though cooling has left it with little more to do than drift through space and become slightly colder every few million years. Its atmosphere suggests otherwise. There is still energy moving outward from the interior. Gas is still being transported between different pressures and temperatures. Molecules are forming and being destroyed. Water is being removed from the upper atmosphere through condensation. Brightness changes as different regions rotate into view. Some chemical species appear where simple equilibrium calculations say they should be scarce. That is weather. It just happens to be weather on an object without a sun. This makes WISE 0855 particularly interesting because almost all of Earth's familiar weather begins with uneven solar heating. Sunlight warms the ground and oceans. Warm air rises. Cooler air sinks. Water evaporates. Clouds form. Winds redistribute energy between warm and cold regions. Take sunlight away from Earth, and the atmosphere would eventually become a very different place. WISE 0855 never had that problem because its main source of atmospheric energy comes from underneath. The interior is warmer than the atmosphere above it. Heat left over from formation continues to work its way outward. That creates an upward energy flow capable of driving motion, even when no nearby star is shining on the object. Jupiter gives us a useful comparison. Jupiter receives energy from the Sun, but it also emits more energy than it absorbs from sunlight. Some of that extra energy is leftover internal heat, and some is associated with slow contraction and the behaviour of its deep interior. That internal energy contributes to Jupiter's powerful atmospheric circulation. WISE 0855 takes away the external heating almost completely. There is no meaningful day side being warmed by a star. There is no night side cooling after sunset. There is no seasonal movement toward and away from a nearby source of light. The energy is coming up from below across the entire object. That does not mean every part of the atmosphere must look the same. Quite the opposite. Atmospheric flow can naturally develop structures. Jupiter has belts, zones, vortices, storms, and regions with different cloud thicknesses, even though a large part of its internal heat is distributed globally. Rotation organizes moving gases. Convection develops in some areas more strongly than others. Clouds form where temperature, pressure, and composition allow them to form. WISE 0855 is probably doing its own version of this. We simply cannot photograph it. Even a telescope as powerful as JWST sees WISE 0855 as an unresolved source. Its disk is far too small on the sky for us to distinguish one hemisphere from another. If it has a large storm, we do not see the storm. If one region has thicker clouds, we do not see the clouds directly. If there is a band around its equator, there is no image in which we can point to it. Instead, astronomers watch the total infrared brightness of the entire object. If the atmosphere is perfectly uniform, rotation should not change that brightness very much. But suppose one region is slightly warmer, or imagine that clouds in one area block radiation that escapes more easily somewhere else. As the brown dwarf rotates, those different regions come into and out of view. The total brightness changes. Spitzer observed exactly that kind of variability. WISE 0855 was monitored at 3.6 and 4.5 microns during 2 observing periods lasting roughly 23 hours each. The observations were separated by several months. In the first period, its brightness varied by about 4 to 5% from peak to peak. During the second, the amplitude was closer to 3 to 4%. The first set of light curves showed semi-periodic structure, while the second looked more irregular. Those numbers are small enough that you would never notice them by looking at an image. For atmospheric science, they are significant. The brown dwarf is changing as it rotates, or more precisely, the portion of its atmosphere facing us changes enough for the total infrared emission to shift measurably. Now we have a problem that sounds surprisingly like weather forecasting. What caused the changes? Clouds are an obvious suspect. Brown dwarfs are famous for atmospheric clouds. In warmer examples, those clouds can be made from materials such as silicates and iron. As temperatures fall, the cloud chemistry changes. At the temperatures of the coldest white dwarfs, water becomes one of the most important possible condensates. WISE 0855 is cold enough that water should be able to leave the gas phase and form ice particles in appropriate atmospheric layers. This possibility attracted attention almost immediately after the object's discovery. An early near-infrared study in 2014 compared observations of WISE 0855 with atmospheric models. Cloudless models struggled to reproduce its extreme colours, while models containing partial cloud cover, including water ice clouds, performed better. The researchers suggested that WISE 0855 might provide the first evidence for water clouds beyond the solar system. That was an exciting possibility. It was not the end of the story. Later observations complicated it. The Spitzer variability study noted that theoretical models had predicted particularly strong mid-infrared brightness changes. Once water ice clouds appeared in objects colder than roughly 375 Kelvin, if water clouds were the main cause of WISE 0855's variability, its relatively modest brightness changes could imply that the two visible hemispheres did not differ very much in their overall cloud coverage. There was another possibility. WISE 0855's variability amplitudes were not dramatically different from those of somewhat warmer brown dwarfs, where water clouds were not expected to dominate. That could mean the same underlying mechanism was creating variability across all of them, rather than water clouds suddenly becoming responsible only in the coldest object. The researchers concluded that robust evidence for water ice clouds was not yet available. This is a good example of how the word evidence changes as observations improve. A model can fit existing data better than its competitors. That is useful. But if several different physical situations can produce similar measurements, the interpretation remains uncertain. Imagine looking outside in the morning and seeing that the pavement is wet. Rain is a good explanation, but perhaps a sprinkler ran during the night. Perhaps someone washed the pavement. Wet ground is evidence that water was involved. It is not automatically proof of rain. WISE. 0855 presented a similar problem. Its infrared colours could be reproduced by models containing clouds. Its brightness varied in ways that could be related to uneven cloud coverage. Its temperature was low enough that water condensation should occur. All of that made water clouds reasonable, but astronomers still wanted the atmospheric equivalent of actually seeing the rain. JWST has now moved much closer to that. The mid-infrared spectrum obtained with MIRI covers wavelengths that probe the atmospheric region where water is expected to condense. Researchers found that the abundance of water vapour falls with altitude. At deeper, warmer levels, more water remains in gaseous form. Higher up, where temperatures are lower, the amount of gaseous water decreases. That is what you expect when water is condensing out of the atmosphere. Earth does this constantly. Warm air can hold more water vapour. Cool that air enough and it eventually reaches saturation. Some of the vapour condenses into droplets or freezes into ice crystals. The total amount of gaseous water falls because some of it has moved into a condensed phase. WISE. 0855 appears to show the same general chemical consequence. The details are very different naturally. There is no familiar terrestrial sky. The background gas is dominated by hydrogen and helium. Pressures can be much greater than those in Earth's cloud-forming regions. Temperatures and gravitational conditions differ. But H2O still responds to temperature according to the same physical principles. Cool the gas sufficiently and water does not remain entirely as vapour. That makes the JWST result important. Water condensation is no longer merely something predicted from the object's overall temperature. The measured vertical abundance of water behaves in the way condensation predicts, yet there is a wonderfully inconvenient detail. The researchers still did not find an unmistakable spectral signature of the water ice cloud particles themselves, so water appears to be condensing. Water ice clouds are physically expected, but the clouds are not standing up in the spectrum and waving. There are several possible reasons. Cloud particles may have sizes that produce weak or broad spectral effects. The clouds may lie at pressures where other molecular absorption hides their signature. Their coverage may be patchy. They may be optically thinner than some models assumed. Or the current atmospheric models may still be missing details. Clouds are difficult even on planets we can visit. Ask a meteorologist to model every droplet inside one terrestrial storm, and you will quickly discover that water has a talent for creating complicated problems. Trying to model ice clouds on a brown dwarf 7 light-years away is not an easier version of that task. Particle size matters. Particle shape matters. How efficiently particles form matters. How quickly they settle downward matters. Atmospheric motion matters. A rising parcel of gas can carry vapour to colder regions where condensation begins. Ice particles may then grow. Gravity pulls them downward. Turbulence can keep smaller particles suspended. Larger particles settle more efficiently. Meanwhile, new vapour arrives from below. A cloud is therefore not simply a layer you switch on in a computer model. It is the result of several competing processes. For WISE, 0855, gravity may be several times stronger than Jupiter's depending on its true mass and radius. That can affect how quickly particles fall. vertical mixing can work in the opposite direction by transporting material upward. Somewhere between those processes, a cloud distribution develops. If the circulation changes, the clouds can change. If the clouds change, the spectrum changes. And if different regions contain different clouds, rotation can produce the brightness variations Spitzer detected. This is why the irregularity of these variations is interesting. During one observing period, the light curve showed a more recognizable repeating pattern. Months later, the pattern had become less orderly. A perfectly permanent spot on a rotating sphere would produce a strongly repeating signal. Each rotation would bring the same feature back into view. Real weather does not usually cooperate that nicely. Storms evolve, clouds spread, temperature patterns shift, winds move atmospheric structures relative to the rotating body underneath. Multiple features can appear at different longitudes. The resulting light curve changes with time. WISE 0855's changing variability therefore fits naturally with a dynamic atmosphere, even though the available observations do not tell us exactly what the structures are. It may have long-lived features, it may have rapidly evolving ones, it may have several atmospheric patterns interacting. The data reveal inhomogeneity, not a weather map. Rotation itself is another difficulty. If we knew the exact rotation period, repeating brightness patterns could be connected more confidently with particular atmospheric structures. Many brown dwarfs rotate quickly, sometimes completing a turn in only a few hours. WISE 0855's faintness makes its period harder to establish cleanly. A 23-hour observing run sounds long until the light curve changes while you are measuring it. If the atmospheric structures evolve on timescales comparable to the rotation period, identifying one simple repeating cycle becomes difficult. It is rather like trying to work out how fast a patterned ball is spinning while someone keeps repainting the pattern. Clouds are only half the weather problem. Chemistry is moving too. Deep in the atmosphere, temperatures are higher. There, carbon chemistry favours a different balance between carbon monoxide and methane than it does in the colder upper layers. If every parcel of gas remained at one pressure and temperature indefinitely, chemical reactions would eventually bring its composition toward equilibrium. But atmospheric parcels do not remain politely in place. Gas rises, gas sinks, convection transports material. Turbulent mixing carries molecules across pressure levels. A molecule created in a hot, deep region can therefore arrive in a cooler region, before chemistry has time to convert it into whatever molecule would be favoured there. Carbon monoxide is the clearest example in WISE 0855. At the cold temperatures of the observable atmosphere, methane should contain much of the carbon under equilibrium conditions, yet carbon monoxide is present. JWST's NIR spectrum detected CO absorption, confirming earlier ground-based evidence and supporting vigorous vertical mixing. Think of the atmosphere as a very slow chemical kitchen with a very impatient waiter. A dish is supposed to sit for 20 minutes before it is ready. Instead, the waiter grabs it after 5 minutes and carries it upstairs. When it arrives, it still looks like something from the kitchen downstairs because there was not enough time for the final transformation. CO works as that unfinished dish. Its presence at observable levels tells astronomers that material has arrived from deeper regions faster than some chemical reactions can catch up. This allows researchers to estimate a quantity called the eddy diffusion coefficient. The name sounds as though it might involve a gentleman named Eddy, who had an unfortunate experience with diffusion. It does not. It is a way of describing how efficiently turbulent motion mixes material vertically through an atmosphere. Stronger mixing can transport gases farther before chemistry re-equilibrates. By comparing the measured abundances of molecules such as carbon monoxide with chemical models, scientists can constrain how effective that transport must be. The same idea works on Jupiter. Carbon monoxide, phosphine, germane, and other molecules can act as traces of material brought upward from deeper regions. That is one reason WISE 0855 0855 is such a useful bridge between brown dwarf science and giant planet science. The atmospheric techniques overlap. Then phosphine makes everything more difficult. Phosphine, pH 3, forms more readily under hot conditions deep inside hydrogen-rich giant planets and brown dwarfs. Vertical mixing can carry it upward. Jupiter and Saturn both contain phosphine in their atmospheres. Given the evidence for vertical mixing in WIC 0855, atmospheric models expected phosphine to appear there too. Initial JWST work found no obvious detection at the expected strength. More detailed retrieval analysis subsequently reported phosphine at only about 1 part per billion. That is very little, and it is considerably less than simple disequilibrium models might lead you to expect. Now, the atmosphere gives us an interesting contradiction. Carbon monoxide tells us gases are being mixed upward. Phosphine says that whatever happens to phosphorus during that journey is not behaving as current models predict. Perhaps phosphine is being destroyed through chemical pathways that are not fully represented. Perhaps phosphorus becomes locked into another compound. Perhaps clouds or condensates remove it. Perhaps the reaction rates at these temperatures need improvement. The important point is not that astronomers have no idea what is happening. They have several ideas. The important point is that the atmosphere has supplied a measurement capable of distinguishing between them. That is much more useful than a perfectly obedient model. Methane creates its own complications. At WIS 0855's temperature, methane should be abundant, and it is. Its absorption dominates important portions of the infrared spectrum. But accurate methane spectra are difficult to model across the enormous range of pressures and temperatures found in brown dwarf atmospheres. Laboratory measurements cannot reproduce every condition directly. Quantum calculations must predict huge numbers of molecular transitions. At high spectral resolution, even tiny inaccuracies in molecular data can affect the final atmospheric interpretation. JWST has made this problem more noticeable because the observations are now better. Before JWST, a slightly inaccurate methane model might hide inside noisy data. Now the telescope can expose discrepancies. Improved observations therefore create a mildly irritating situation in which the instrument succeeds so well that the theoretical calculations start looking worse. This is considered progress. Water, methane, ammonia, carbon monoxide and phosphine are not the only chemical clues available. JWST has become sensitive enough to distinguish isotopologues, molecules containing different isotopes of the same elements. Researchers using WIS 0855's NIR spec data have detected deuterated methane, CH3D, allowing them to estimate the ratio of deuterium to ordinary hydrogen outside the solar system in a substellar atmosphere. The inferred ratio is consistent with a roughly protosolar abundance, supporting the idea that WIS 0855 did not burn away much of its original deuterium and is therefore very low in mass. Another JWST analysis detected ammonia containing nitrogen-15 and measured the ratio between the common nitrogen-14 ammonia and this rarer version. These measurements are not weather in the same way clouds and circulation are. They are closer to chemical fingerprints of origin, but weather determines where molecules appear and whether they can be measured. The atmosphere mixes material. Condensation removes some species from the gas. Chemical reactions transform others. A spectrum therefore contains several stories at once. Some features tell you what the object was made from. Others tell you how hot it is. Others reveal how gas is moving now. Others show what is condensed. Separating those stories is one of the hardest parts of atmospheric science. Suppose the amount of water vapour looks lower than expected. Maybe water is condensed into clouds, or perhaps the brown dwarf simply formed with less oxygen. Perhaps the temperature profile differs from the model. Perhaps vertical mixing has changed the distribution. A single measurement can have several explanations. Researchers therefore fit many wavelengths simultaneously. If one interpretation explains the water feature, but ruins the methane feature, it is not very useful. A successful model has to reproduce as much of the full spectrum as possible. JWST's broad coverage from the near-infrared into the mid-infrared is especially powerful because different wavelengths sample different atmospheric depths. At one wavelength, you may be seeing radiation escaping from a relatively high, cool level. At another, you may be receiving photons from deeper and warmer layers. This means researchers can begin reconstructing a vertical temperature profile. They can ask where condensation occurs. They can determine whether a molecule's abundance remains constant with altitude or changes. The water result is a particularly clear demonstration. A model with one fixed water abundance throughout the atmosphere does not capture everything in the observations. Allowing the abundance to decrease at higher levels gives a better physical description, consistent with water being removed from the gas as it condenses. That gives us a rough atmospheric journey. Start deep. The pressure is high, the temperature is high enough for water to remain vapor. Move upward. The atmosphere expands and cools. Eventually conditions cross the water condensation curve. Some vapor becomes ice. Continue upward and less gaseous water remains. At the same time, methane and ammonia absorb radiation. Carbon monoxide carries evidence from hotter depths, and the entire structure is being stirred by circulation. No sunlight is required. The weather is powered by the object's slow loss of internal energy. How violent might that weather be? This is where we have to be careful. It is tempting to imagine an enormous storm simply because Jupiter has its snormous storms. WISE 0855 could indeed possess large-scale atmospheric features, but current observations do not allow us to say that there is a great red spot equivalent or a particular wind speed racing around its equator. Brightness variability tells us that different regions are not identical. It does not give us a direct measurement of individual storms. Atmospheric models can predict circulation patterns, but predictions are not photographs. So the safest picture is a dynamic one without pretending we know the detailed map. There are temperature differences. There are likely variations in cloud properties or opacity. Material is mixed vertically. The appearance changes with time. Water condenses in the upper atmosphere. That is already enough to justify calling the weather active. The phrase wild weather does not need lightning bolts and hurricanes to be interesting. On WISE 0855, the unusual part is the physical setting. Imagine weather occurring on an object with no surface beneath it and no sun above it. Descend far enough and the atmosphere simply becomes a hotter, denser fluid. Rise high enough and pressure drops while water begins disappearing from the gas. Cloud particles may form and settle. Methane remains abundant. Ammonia produces strong infrared features. Carbon monoxide arrives from somewhere warmer below. The entire system rotates in darkness while radiating heat left over from an object that may be billions of years old. There is nothing on Earth quite like that. Jupiter comes closer. Its 5-micron spectrum in particular provides an important comparison, because radiation at those wavelengths escapes from relatively deep atmospheric regions. Early spectroscopy of WISE 0855 found similarities with Jupiter around this wavelength, including water absorption. That resemblance helped establish the idea that the coldest brown dwarfs are useful analogues for giant planets. The comparison has only become stronger as JWST has revealed more molecules, but there are differences worth keeping. WISE 085. 5 may be several times Jupiter's mass. Its surface gravity could be stronger. Its atmosphere receives essentially no stellar radiation. Its formation history may have been completely different. Its elemental abundances may not match Jupiter's, so rather than calling it a second Jupiter, it is better to think of it as a natural experiment. What happens when you take a self-luminous body with roughly planetary dimensions, give it several Jupiter masses, isolate it from a star, and allow it to cool into a temperature regime where water can condense? WISE 085. 5 is one answer. And that answer may tell us how other objects behave that are much harder to observe. A giant exoplanet orbiting several astronomical units from another star could have temperatures similar to WISE 0855. Its atmosphere might contain the same major molecules. Water might condense. Methane could dominate carbon chemistry. Vertical mixing might preserve carbon monoxide and phosphine. The difficulty is that the host star would be sitting nearby, producing vastly more light. WISE 0855 removes that problem. There is no star to subtract. No stellar spectrum contaminating the observation. No need to separate a planet from a bright point only a fraction of an arcsecond away. We receive the object's own thermal radiation directly. That makes every strange bit of weather useful beyond WISE 0855 itself. If atmospheric models cannot reproduce its water depletion correctly, we should be cautious about using the same models for cold exoplanets. If phosphorus chemistry fails here, it may fail elsewhere. If methane absorption is incomplete, future planetary spectra will inherit the same problem. If cloud models predict a feature that WISE 0855 does not show, the cloud physics needs attention before we confidently apply it to a world orbiting another star. In that sense, WISE 0855 is doing the job of a test laboratory, a rather inconvenient laboratory because it is 7 light-years away and refuses to provide samples, but a laboratory nonetheless. The next generation of observations may eventually monitor it spectroscopically as it rotates, rather than measuring only broad brightness changes. That would allow astronomers to ask whether water absorption becomes stronger or weaker when a particular region turns toward us. They could see whether methane varies with the same pattern. They could determine whether deeper atmospheric layers change differently from higher ones. If one wavelength brightens while another dims, that could help reconstruct the vertical structure of a cloud or temperature anomaly. Instead of one unresolved light curve, we would begin obtaining something closer to 3-dimensional weather information, not a photograph, more like tomography. Medical scanners reconstruct the inside of a body from indirect measurements taken from different angles. Brown dwarf weather mapping uses a similarly indirect idea. As the object rotates, atmospheric structures modulate its spectrum. With enough precise observations and suitable models, those changes can constrain where the structures are and which pressures they affect. WISE 085. 5 is difficult enough that this remains challenging, but JWST has moved the possibility much closer. For now, the information we already have gives us a surprisingly busy atmosphere. Water vapor is present and decreases in the upper layers in a manner consistent with condensation. Clear direct spectral evidence for the resulting water ice particles remains elusive. Infrared brightness changes by several %, demonstrating that the visible atmosphere is not uniform and that its patterns can evolve over periods of months. Carbon monoxide reveals vertical mixing. Phosphine exists at unexpectedly low abundance. Methane and ammonia dominate important pieces of the spectrum. Rare isotopic forms of methane and ammonia are measurable. All of that is happening in something that was once easy to describe casually as a failed star. The closer we look, the less satisfying that description becomes. Failed stars are supposed to sound like stellar objects that did not quite make it. WISE 0855 now looks much more like a giant planetary atmosphere that happens to have formed independently. Its temperature overlaps with planets, its size is roughly planetary, its clouds involve water, its carbon chemistry involves methane and carbon monoxide. Its atmospheric motion can be studied with the same disequilibrium techniques used for Jupiter. Even its weather variability invites direct comparison with giant planets. And yet its origin appears to place it with brown dwarfs rather than ordinary planets. That leaves us exactly where objects like WISE 0855 seem most comfortable, between categories. The more accurately we measure it, the harder it becomes to draw a simple physical line separating the smallest brown dwarfs from the largest free-floating planets. Does nature itself provide a clear boundary between a brown dwarf and a giant planet at all? The boundary between a brown dwarf and a giant planet becomes especially awkward when the object sitting on that boundary is WISE 0855-0714. If we place the Sun, one of the smallest true stars, WISE 0855, and Jupiter beside one another, the first comparison would seem straightforward. The Sun would obviously be the star, Jupiter would obviously be the planet, UICO 855 would be the troublesome one in the middle. The Sun contains enough mass to maintain hydrogen fusion in its core. Even the smallest ordinary stars can do the same thing, although they manage it far more slowly. Modern calculations place the minimum mass for sustained hydrogen burning near 0.075 times the mass of the Sun for roughly solar composition, which works out to around 78 or 79 Jupiter masses. Below that region, an object can become hot during formation, but cannot settle into the long-lasting hydrogen fusion that defines an ordinary main sequence star. WISE 0855 is nowhere close to that boundary. Estimates based on its luminosity and evolutionary models have placed it at roughly 1.5 to 8 times Jupiter's mass across a broad range of possible ages. Earlier estimates often gave slightly wider ranges, but either way, we're not talking about an object that almost became a hydrogen-burning star. It missed that particular appointment by quite a distance. That alone makes the phrase failed star a little misleading. Imagine entering a marathon, stopping after the first kilometre, catching a bus home, and then being described for the rest of your life as an almost marathon winner. Technically, there was a route from one situation to the other. Practically, the distance between them matters. WISE 0855 is so low in mass that its present physical properties overlap much more comfortably with giant planets than with even the smallest true stars. Its size provides the first surprise. A star with far more mass than Jupiter does not necessarily have a proportionally larger radius when we enter the brown dwarf regime. Brown dwarfs and giant planets are made largely from compressible hydrogen and helium. Add more mass, and gravity pushes the material together more strongly. The object becomes denser. It does not simply inflate like a larger balloon. At high pressures, electron degeneracy also becomes increasingly important in resisting further compression. The result is that objects ranging from giant planets through much of the brown dwarf mass range can all remain roughly comparable to Jupiter in radius. So if you could somehow place WISE 0855 beside Jupiter, you might initially be disappointed by the size difference. You would not see a giant sphere 10 times wider, simply because WISE 0855 contains several times more mass. They could be broadly similar in diameter. The real difference would be hidden in how much material is packed inside. Take roughly Jupiter's size, add several Jupiters worth of mass, let gravity compress the result, then leave it alone in interstellar space for perhaps billions of years. You begin to approach WISE 0855. That stronger gravity would also affect anything attempting to enter the atmosphere. There is no solid surface where you could step onto a bathroom scale, but the acceleration produced by gravity in its observable atmospheric regions is expected to be greater than Jupiter's for many of the plausible mass and radius combinations. Cloud particles would feel that gravity. Atmospheric pressure would change rapidly with depth. Material settling from clouds could behave differently from the same particles in Jupiter's atmosphere. Even if two objects have almost the same temperature, their weather does not have to be identical if one is substantially more massive. Temperature gives us another useful comparison. Jupiter is very cold by everyday standards. Measurements of its thermal emission give it an effective temperature of roughly 124 Kelvin, considerably colder than the approximately 260 to 285 Kelvin range associated with WISE 0855. Jupiter nevertheless emits more thermal energy than it receives from the Sun, showing that internal heat still escapes from the planet more than 4.5 billion years after its formation. WISE 0855 is therefore not colder than Jupiter. That point is easy to lose when it receives labels such as the coldest known brown dwarf, or, less accurately, the coldest star. It is cold compared with brown dwarfs. It is extraordinarily cold compared with stars. Compared with the giant planets of our own solar system, it is actually warmer. That makes the comparison much more useful. WISE 0855 occupies a temperature range that begins connecting the brown dwarf population with the temperatures of giant planets. Move upward in temperature and you find warmer Y dwarfs, then T dwarfs, then L dwarfs, eventually approaching the smallest stars. Move downward and you begin approaching worlds such as Jupiter. WISE 0855 sits in between, allowing astronomers to test whether atmospheric models developed for brown dwarfs continue working as conditions become increasingly planetary. Its atmosphere immediately makes the resemblance obvious. Jupiter and WISE 0855 are both dominated by hydrogen and helium. Both contain water, both contain methane, both contain ammonia, both have carbon monoxide that can tell us about transport from deeper, hotter atmospheric regions. Both contain cloud physics and chemistry that depend strongly on pressure and temperature. On paper, the ingredient lists begin looking surprisingly similar. Put the spectra beside one another, however, and differences appear. Jupiter is being irradiated by the Sun. Dostoevsky 0855 effectively is not. Jupiter's upper atmosphere, clouds, and photochemistry are influenced by incoming sunlight, ultraviolet radiation, charged particles, and the interaction between the solar wind and its enormous magnetic environment. WISE 0855 has no nearby star providing an equivalent external energy source. Its thermal radiation is largely energy escaping from within. That difference alone changes the experiment. Jupiter is a giant planet receiving energy from above while also releasing energy from below. WISE 0855 is much closer to a purely self-luminous atmosphere, where the important energy flow comes upward from the interior. For atmospheric physicists, that is wonderfully convenient. It removes one major variable. Imagine wanting to understand how a house loses heat while someone keeps shining an enormous heat lamp through one window. Turn off the lamp and the problem becomes easier to isolate. WISE 0855 has very helpfully misplaced the lamp. Its chemistry also shows differences that current models are still trying to explain. Carbon monoxide has been detected in WISE 0855, indicating that material is being transported upward from hotter atmospheric layers quickly enough for the chemistry to remain out of equilibrium. Methane is abundant, as expected at these low temperatures. Water and ammonia are also prominent in JWST spectra. Phosphine provides a more curious contrast. Jupiter contains significant phosphine because phosphorus-bearing material from hot, deeper regions is mixed upward before the molecule can be completely destroyed. A similar process was expected to produce noticeable phosphine in very cold brown dwarfs. WISE 0855 refused to cooperate. The newest retrieval work has found phosphine at only around 1 part per billion, far less than straightforward models had expected despite clear evidence that vertical mixing is occurring. So Jupiter and WISE 0855 can have similar temperatures and broadly similar atmospheric ingredients, while still producing different chemical outcomes. That is exactly why comparing them is scientifically useful. If they were identical, there would be less to learn. The differences force researchers to ask whether gravity matters, whether elemental composition differs, whether phosphorus condenses into other compounds, whether chemical reaction rates are incomplete, or whether the vertical circulation behaves differently. Then there is water. Jupiter is believed to have water clouds beneath higher cloud layers, while WISE 0855 is cold enough for water condensation to occur in the atmospheric region, accessible to infrared observations. JWST measurements show that gaseous water becomes depleted higher in WISE 0855's atmosphere, matching what is expected when water condenses. Direct, unmistakable spectral signatures of the water ice particles themselves have remained elusive, but the condensation process is increasingly well constrained. Again, the resemblance to a planet becomes difficult to ignore. We're no longer discussing the sorts of clouds associated with hot stellar objects. We're discussing water-changing phase inside a cold, hydrogen-rich atmosphere. If we knew nothing about the object's origin and simply received a list containing its size, estimated mass, temperature, and atmospheric molecules, calling it a giant planet would not sound unreasonable. That brings us to the most commonly mentioned dividing line between planets and brown dwarfs: deuterium. Ordinary hydrogen is made from a single proton. Deuterium contains a proton and a neutron. It is still hydrogen, but the heavier nucleus can undergo fusion at lower temperatures than ordinary hydrogen. Objects near roughly 13 Jupiter masses can become hot enough in their interiors to burn significant amounts of deuterium early in their lives. For many years, that value has been used as a convenient dividing point. Below 13 Jupiter masses, call it a planet. Above 13 but below the hydrogen burning limit, call it a brown dwarf. Simple. Unfortunately, nature has once again failed to respect the filing system. The deuterium burning threshold is not exactly 13 Jupiter masses. Detailed calculations show that it depends on helium abundance, metallicity, the original amount of deuterium, and even what percentage of deuterium you decide must be burned before you declare that deuterium burning has occurred. Depending on those assumptions, the relevant mass can range from roughly 11 to more than 16 Jupiter masses. So 13 Jupiter masses is useful as a rule of thumb. It is not a wall built into the universe. More importantly, whether an object burns deuterium for a short period tells us surprisingly little about how that object formed. Imagine two bodies. One forms from the gravitational collapse of a small gas cloud completely by itself and ends up with 12 Jupiter masses. Another grows inside a disk surrounding a young star and reaches 14 Jupiter masses. Under a strict 13 Jupiter mass rule, the independently formed object becomes a planet while the disk-formed companion becomes a brown dwarf. That may be convenient for a table. Physically, it feels backward. For this reason, many researchers prefer to think about formation as well as mass. Stars and brown dwarfs are generally associated with gravitational collapse and fragmentation of gas clouds. Planets are generally associated with material assembling within disks around young stars, through processes such as core accretion or gravitational instability within the disk. Under a formation-based description, the 12 Jupiter mass isolated object could be a brown dwarf, while the 14 Jupiter mass companion might still reasonably be discussed as a massive planet. Even professional definitions acknowledge that the distinction is not perfect. The International Astronomical Union's current working definition for exoplanets uses the deuterium fusion boundary for objects orbiting stars, brown dwarfs, or stellar remnants, while scientific literature continues to emphasize that the physical divide between planets and brown dwarfs is not universally agreed upon. WISE. 0855 makes this ambiguity particularly obvious because its estimated mass is probably below the traditional deuterium burning threshold. If mass were the only criterion, you might be tempted to call it planetary. Its atmosphere certainly would not object, its temperature would not object, its radius would not object. But there is a problem. A planet normally belongs to a planetary system, or at least once belonged to one. WISE. 0855 has no known host star. It is moving independently through space. That leaves two broad possibilities. Perhaps it formed directly from a collapsing cloud through the low mass extension of brown dwarf formation, or perhaps it originally formed as a planet around a star and was later ejected. Planetary systems can be chaotic when young. Multiple giant planets can gravitationally scatter one another. A close encounter can throw one planet inward, push another outward, and in extreme cases eject a planet completely from the system. The expelled world then becomes a free-floating or rogue planet, travelling through the galaxy without its original star. If WISE 0855 had such a history, its present isolation would not tell us. The star could now be nowhere nearby. After billions of years, reconstructing the event would be extremely difficult. This produces a wonderfully inconvenient possibility. A rogue giant planet and a low-mass brown dwarf could look almost identical today. Both could be roughly Jupiter-sized. Both could have several Jupiter masses. Both could have temperatures of a few hundred Kelvin. Both could contain hydrogen, helium, methane, ammonia, water, and carbon monoxide. Both could drift alone. Both could lack sustained fusion. One would be a planet because of its birth. The other would be a brown dwarf because of its birth. And unless we witnessed those births, distinguishing them might require very subtle clues. Composition could help. A planet growing inside a protoplanetary disk may become enriched in heavy elements relative to the star because it accretes solids, ices and gas in different proportions. A brown dwarf forming directly from a collapsing cloud might retain a composition closer to the interstellar material from which it formed, so atmospheric metallicity, carbon to oxygen ratios and isotopic ratios could contain hints. JWST has begun measuring exactly the kind of information that might eventually help. Deuterated methane has now been detected in WISE 0855, allowing researchers to estimate its deuterium to hydrogen ratio. The result is consistent with a roughly protosolar abundance, and supports the conclusion that the object is low enough in mass that it did not substantially destroy its original deuterium. That tells us something important about its mass and evolution. It does not hand us a birth certificate. The same is true of the nitrogen isotope measurements obtained from ammonia. Such measurements may become valuable formation tracers when astronomers can compare many brown dwarfs, exoplanets, giant planets, and planet-forming disks. At the moment, one ratio in one unusual object does not provide enough information to reconstruct exactly how WISE 0855 formed, so the label remains useful but imperfect. Physically, perhaps the easiest way to understand WISE 0855 is to imagine a continuous scale. At one end, place the Sun. Its enormous mass produces sustained hydrogen fusion. Move downward and the stars become smaller, cooler, dimmer, and longer-lived. Eventually you reach the smallest red dwarfs, hovering just above the hydrogen-burning limit. Drop below roughly 78 Jupiter masses and sustained hydrogen fusion stops. Now we are among brown dwarfs. Continue downward through dozens of Jupiter masses. Some of these objects burn deuterium briefly. Continue farther. Deuterium burning becomes limited and then disappears. Their sizes remain roughly planetary. Their atmospheres cool. Methane strengthens. Ammonia becomes important. Water can eventually condense. By the time we arrive at WIC 0855, we may be dealing with only a handful of Jupiter masses and a temperature around 270 Kelvin. Move a little farther along and you reach giant planets such as Jupiter. Nothing suddenly changes colour. No warning light comes on. There is no sign floating in space saying, "Brown dwarfs end here." The transition is gradual. The largest distinction may be historical rather than visible. How did the object form? Was it created by the same fragmentation process that forms stars and brown dwarfs? Or did it assemble inside the disk of another object? That is why WISE 0855 is more interesting than a simple record holder. Its existence tests whether the categories astronomers inherited from studying bright stars and familiar planets remain useful once we discover objects that occupy the gap. From a stellar perspective, WISE 0855 is extraordinarily low mass, exceptionally cold, and incapable of ordinary hydrogen fusion. From a planetary perspective, it is roughly Jupiter-sized, several times Jupiter's mass, rich in familiar giant planet molecules, and only moderately warmer than some solar system planets. From an atmospheric perspective, the distinction almost disappears. A molecule of methane does not behave differently because astronomers filed the object under brown dwarf instead of planet. Water condensation does not ask how the object formed. Carbon monoxide responds to temperature, pressure, and mixing. Cloud particles respond to gravity. Radiation responds to opacity. Physics continues working while we argue about terminology. There is one comparison with Jupiter that makes this particularly clear. Suppose we could magically move Jupiter away from the Sun. We would have to move its moons with it if we wanted to avoid an unusually complicated afternoon. But ignore those for the moment. Take Jupiter and place it alone between the stars. Sunlight would disappear. The reflected light that makes Jupiter so bright through a telescope would vanish. Its atmosphere would begin responding to the loss of external heating. But Jupiter would not immediately become dark and frozen throughout. It contains internal heat. It would continue emitting infrared radiation. Given immense spans of time, it would cool further. From several light years away, our best way to find it would eventually be the same basic method used for the coldest brown dwarfs. Search for weak infrared emission and watch for motion against the distant background. An isolated Jupiter would therefore begin looking observationally more like the population to which WISE 0855 belongs. Now reverse the comparison. Imagine WISE 0855 orbiting a star at the distance Jupiter orbits the Sun. Suddenly it would receive external radiation. Its upper atmosphere would change. Photochemistry could become important. Its temperature structure would no longer be controlled almost entirely by internal heat. To a distant astronomer, it might appear to be an unusually massive giant planet. The object's physics would remain the same. The context would change the label. That is one reason astronomers increasingly use terms such as planetary mass object when they want to describe what something is without pretending they know precisely how it formed. WISE 0855 can comfortably occupy that description. Its mass is planetary. Its radius is planetary. Its temperature is planetary. Its likely formation places it among brown dwarfs. None of those statements has to cancel the others. It can be a brown dwarf and still teach us about planets. In fact, that is exactly what makes it valuable. Cold giant exoplanets are difficult to study because their host stars overwhelm them. A Jupiter analogue around another star may be billions of times fainter than the star at visible wavelengths, and even in the infrared the contrast and angular separation create major observational challenges. WISE 0855 has no bright stellar companion beside it. Its atmosphere is presented almost by itself. That means astronomers can obtain spectra of a cold planetary mass atmosphere without first fighting the glare of a nearby sun. Recent research explicitly treats the coldest white dwarfs as atmospheric proxies for cool and warm giant exoplanets in roughly the 200 to 400 Kelvin range. WISE 0855 is especially valuable because its temperature and mass overlap the regime astronomers ultimately want to study in mature giant planets. It is effectively giving us practice. We can test methane models, we can test ammonia chemistry, we can search for water condensation, we can measure carbon monoxide and estimate vertical mixing. We can discover that phosphine behaves differently from our predictions. We can examine isotopes. We can compare cloud models against a real spectrum instead of a computer simulation. Then, when telescopes eventually obtain equally detailed spectra of cold giant planets orbiting other stars, the interpretation will not have to begin from scratch. This also changes the way we should think about the objects still waiting to be found. WISE 0855 was difficult to discover despite being only about 2.28 parsecs, or roughly 7.4 light years, away in the refined distance measurements used by recent studies. It is faint because cold planetary mass bodies release very little radiation, not because such bodies must be rare. There could be other isolated objects occupying the same boundary. Some may be brown dwarfs formed directly from collapsing gas. Some may be planets expelled from systems long ago. Others may sit so close to the traditional dividing lines that the distinction becomes largely a matter of which definition an astronomer chooses. They would all be difficult to see, and WISE 0855 has already shown us that difficult to see is not the same thing as far away. A dark object can sit in the local stellar neighbourhood for most of human history without appearing in ordinary telescopes. Once that becomes clear, the comparison between WISE 0855, Jupiter, planets and stars starts pointing toward a larger question. If one planetary mass object could remain almost invisible only a few light-years from the Sun, how complete is our picture of the population wandering between the stars? Finding more of those hidden worlds will require better surveys, but understanding the one we already have requires something slightly different. It requires taking the tiny amount of infrared radiation coming from WISE 0855-0714 and examining it closely enough that individual molecules begin to reveal themselves. That is where the James Webb Space Telescope has changed the situation. Before Webb, astronomers already knew a surprising amount about WISE 0855. WISE had found it. Spitzer helped establish its distance and infrared brightness. Ground-based telescopes had pushed observations to the point where a spectrum around 5 microns could finally be obtained. Researchers knew that the object was extremely cold, that it had a mass somewhere in the planetary range according to evolutionary models, and that its atmosphere probably contained water and other molecules familiar from giant planets. The problem was that many of those conclusions were being assembled from narrow spectral regions, broadband measurements, upper limits, and models that did not always agree with one another. WISE 0855 was giving us clues. Webb began giving us sentences. Its near-infrared spectrograph, or NIR spec, observed the object across roughly 1 to 5 microns with far greater sensitivity, wavelength coverage, and spectral resolution than had previously been available. The first published NIR spec analysis described the improvement as dramatic and found that a cloudless atmospheric model with an effective temperature of about 285 Kelvin provided a useful preliminary fit, although that temperature was roughly 20 Kelvin warmer than one estimate derived from luminosity and evolutionary models. That discrepancy is not merely an argument over whether the object would prefer a slightly thicker coat. Temperature estimates in astronomy often depend on assumptions about radius, gravity, atmospheric structure, and how efficiently radiation escapes. If one method says approximately 285 Kelvin and another suggests something closer to the mid-260s, researchers do not simply average the numbers and head home. They ask why the methods disagree. Perhaps the assumed radius is slightly wrong. Perhaps the temperature structure differs from the model. Perhaps an atmospheric process has not been represented correctly. The mismatch itself becomes information. This is particularly important for WISE 0855, because atmospheric models at these temperatures are being pushed into a regime where relatively few objects have been measured well. You can build a model of a 270 Kelvin hydrogen-rich atmosphere. You can include methane, water, ammonia, carbon monoxide, clouds, convection, vertical mixing, and gravity. But until you compare that model with a real object, it remains a calculation. WISE 0855 is the test, and Webb is now providing enough spectral detail that the test is becoming rather strict. One of NIR spec's clearest results involved carbon monoxide. CO had already been suggested in earlier ground-based observations, but Webb detected absorption from its fundamental band much more convincingly. At the cold temperatures of the observable atmosphere, equilibrium chemistry would prefer much of the carbon to reside in methane. Finding carbon monoxide therefore points toward material being transported upward from hotter regions before chemical reactions can fully convert it. This means Webb is not merely identifying a molecule, it is detecting evidence for motion. A photon leaves WISE 0855, travels for more than 7 years, enters Webb, passes through NIR spec, and ultimately contributes to a spectral feature telling astronomers that somewhere inside that distant object, gas is being moved vertically. There is something wonderfully practical about that. We cannot see the circulation. We cannot place an instrument inside it. We cannot release a weather balloon and ask it to radio back the pressure. But chemistry acts as a tracer. Carbon monoxide has effectively brought information from deeper in the atmosphere with it. Webb also complicated one of the more famous ideas about WISE 0855. Water ice clouds had been suggested by earlier observations and atmospheric modelling, and the possibility was especially exciting because WISE 0855 is cold enough for water to condense. The initial NIR spec work, however, found that the spectral region previously associated with evidence for water ice clouds could be reproduced surprisingly well by a cloudless model. The researchers therefore concluded that a clear water ice cloud detection had not yet been established. That sounds like Webb removed the clouds. It didn't. A model fitting without clouds does not mean no clouds exist. It means the available spectral feature was not sufficient to require them. Then Webb's mid-infrared instrument, MIRI, added a much larger piece of the atmosphere. MIRI observations were combined with the NIR spec data to produce a spectrum extending from approximately 0.8 to 22 microns. This broader wavelength coverage captures a much larger fraction of WISE 0855's total emitted energy and samples atmospheric layers that shorter wavelengths alone cannot probe. The resulting analysis found something particularly interesting about water. The amount of water vapor decreases with altitude. Deeper down, where the atmosphere is warmer, water can remain gaseous. Higher up, temperatures become low enough for water to condense. When that happens, water leaves the gas phase, so less water vapor remains above the condensation level. The measured vertical water profile behaves in just that way. In other words, Webb can see the atmospheric consequence of water condensation. Yet even with the MIRI spectrum, the researchers did not find the unmistakable spectral fingerprints of water ice cloud particles that some earlier models had predicted. So we now have a wonderfully specific situation. Water is there, water is condensing. The atmospheric abundance changes in the expected direction. Water ice clouds should form under those conditions, but the clouds themselves remain spectroscopically shy. That may turn out to be a problem with particle sizes, cloud thickness, altitude, incomplete cloud models, or simply the fact that molecular absorption hides the relevant signatures. Whatever the explanation, Webb has moved the question from "could water clouds exist?" to something much more useful. If water is condensing, why don't the resulting particles affect the spectrum exactly as predicted? That is a better scientific question. Webb has also measured ammonia in impressive detail. MIRI spectroscopy allowed researchers to identify an isotopic version of ammonia containing nitrogen-15 rather than the much more common nitrogen-14. From those features they estimated the relative abundance of the two ammonia isotopologues. It is worth considering how absurdly difficult that would have sounded not very long ago. WISE 0855 itself was not announced until 2014. It was so faint that simply detecting it at some wavelengths was difficult. A decade later, researchers were distinguishing molecules that differ only in which isotope of nitrogen sits inside them. The brown dwarf has not moved closer. The instrument has become better. Another Webb analysis detected deuterated methane, CH3D. Ordinary methane is CH4, one carbon atom surrounded by four ordinary hydrogen atoms. In deuterated methane, one of those hydrogen atoms is replaced by deuterium, the heavier isotope of hydrogen. That small mass difference slightly changes the molecule's spectral behaviour. With NIR spec, researchers were able to measure it and infer the deuterium to hydrogen ratio of WISE 0855's atmosphere. The result was consistent with a roughly protosolar abundance and provided evidence that the object had not substantially destroyed its original deuterium through nuclear burning. That connects atmospheric spectroscopy directly to the question of mass. Objects massive enough to reach sufficiently high internal temperatures can burn deuterium early in their histories. Objects well below that threshold preserve it. WISE 0855 appears to have preserved a large amount of its original deuterium. That supports the picture of a very low-mass object, and once again, the boundary between brown dwarf and planet becomes uncomfortable. We have an isolated body that is generally classified as a brown dwarf. Yet its atmospheric deuterium is consistent with an object below the regime where substantial deuterium burning would occur. Its temperature is comparable with those expected for cool giant planets. Its radius is approximately planetary. Its likely mass is only several times Jupiter's. Its atmosphere contains methane, ammonia, water, carbon monoxide, and perhaps water clouds. If you were hoping Webb would produce one measurement that neatly settles whether WISE 0855 is really a brown dwarf or really a planet, the universe has declined the invitation. Instead, Webb is showing us why the question is difficult. The physical transition is continuous. Go from a low-mass star downward and sustained hydrogen fusion eventually stops. Continue to lower masses and some brown dwarfs can still burn deuterium temporarily. Go lower again, and even that disappears. The objects continue to cool. Their radii remain roughly planetary. Their atmospheres become rich in molecules. Clouds change from exotic high-temperature condensates to substances such as water. Eventually, their observable properties overlap almost completely with those of giant planets. There is no sudden atmospheric transformation at 13 Jupiter masses. Methane does not inspect the object's mass before deciding whether to form. Water does not refuse to condense because the object was born through cloud fragmentation. A spectrum records local physics, temperature, pressure, composition, gravity, mixing, clouds. It does not directly record the label astronomers placed on the object. This is why formation history remains so important. A brown dwarf may form when a cloud or fragment collapses under its own gravity. A giant planet may grow in a disk surrounding a young star. If that planet is later ejected, it can become a free-floating object. After enough time, a low-mass brown dwarf and an ejected giant planet could have similar masses, sizes, temperatures, and atmospheric spectra. Webb may eventually give us chemical clues capable of separating those histories. Isotopic ratios are one possibility. Heavy element abundances are another. Planet formation inside disks can enrich objects in elements heavier than hydrogen and helium in ways that direct gravitational collapse might not. But interpreting those differences requires a large comparison sample. One object is not enough. This is where WISE 0855 becomes useful far beyond itself. The coldest white dwarfs have masses and temperatures overlapping with cool and warm giant exoplanets, roughly in the few hundred Kelvin regime. Researchers explicitly use them as proxies for giant exoplanet atmospheres because they can be observed without the blinding light of a nearby host star. A mature Jupiter-like planet around another star is extremely difficult to study. It may be faint. It may orbit close enough to its star, from our perspective, that separating the two requires exceptional angular resolution. Even if you isolate the planet, collecting a detailed spectrum can demand enormous sensitivity. WISE 0855 removes the stellar contrast problem. 5 removes the "there is no nearby star, nothing is drowning its thermal radiation in glare. It is faint, certainly, but it is faint by itself." That makes it a natural rehearsal for future exoplanet observations. If an atmospheric retrieval technique cannot correctly describe WISE 0855, we should not blindly trust it when applied to an even harder giant planet orbiting another star. If methane line lists produce inaccurate absorption here, they will produce inaccurate absorption there. If cloud physics fails to explain water condensation in WISE 0855, it may also fail in a temperate giant exoplanet. If vertical mixing calculations predict far too much phosphine here, something in the chemistry needs improvement before the same prediction is applied elsewhere. Phosphine is a particularly good example. Initial NIR spec analysis did not detect the amount expected from models of vertically mixed white dwarf atmospheres. A later retrieval using published and additional NIR spec observations did find phosphine, but at only about 1 part per billion. So the molecule is not entirely absent. It is simply much less abundant than straightforward expectation suggested. That creates a chemical puzzle. Carbon monoxide tells us mixing is active. Phosphine says phosphorus chemistry is not responding as predicted. One option is that phosphine is destroyed efficiently along the journey upward. Another is that phosphorus becomes locked into other compounds or condensates. Another is that chemical reaction rates remain incomplete at these temperatures and pressures. Better spectra narrow the possibilities. That is the repeated pattern of Webb's work on WISE 0855. The telescope does not merely add detail to a picture we already understood, it reveals where that picture was too simple. The water cloud story becomes more complicated. The phosphine prediction becomes more complicated. The effective temperature remains somewhat dependent on how it is modelled. The atmosphere refuses to behave as a perfectly mixed column, and non-equilibrium chemistry matters enough that molecules carry information between layers. There is even a newer way Webb has begun using WISE 0855 long-time series spectroscopy. An 11-hour NIR spec dataset has been analysed in a search for transiting moons around the object. No statistically significant moon transit was found in those observations, but the experiment demonstrated that Webb is sensitive to remarkably small transit signals around free-floating planetary mass objects and can separate potential transit features from the object's own atmospheric variability. That may eventually open another route to studying isolated objects like this. If a moon were found orbiting a free-floating brown dwarf or planetary mass object, its orbit could help constrain the system's mass. Moons might also preserve information about formation. A regular system of satellites could indicate a disk once surrounded the object. Different moon architectures might distinguish formation pathways. For now, WISE 0855 has not offered us a confirmed moon. Apparently it felt the atmosphere was already enough homework. What Webb has definitely supplied is a much more complete energy budget. The combined near and mid-infrared spectrum allowed researchers to integrate the object's radiation and determine a bolometric luminosity of about 10 to the power of minus 7.29 times the Sun's luminosity. That is extraordinarily faint. If you want to understand why WISE 0855 remained unknown despite being nearby, this number does much of the explaining. It is not merely dimmer than the Sun, it is millions of times less luminous, and it releases that small amount of energy mainly in wavelengths our eyes cannot detect. Yet those few escaping photons now carry enough information to measure water depletion, ammonia isotopes, deuterated methane, carbon monoxide, phosphine, temperature structure, and total luminosity. There is a useful lesson hidden in that. Astronomy does not always progress by seeing farther. Sometimes it progresses by seeing fainter. WISE 0855 is only about 2.28 parsecs away, roughly 7.4 light-years in the refined distance adopted by recent analyses. It is extraordinarily close compared with almost every object studied in modern astrophysics. The difficulty comes from what it is, not where it is. Webb was often described before launch as a telescope that would study the first galaxies, distant stars, and exoplanets. It does all of those things. But WISE 0855 demonstrates another side of the observatory. Here, Webb is not reaching across 13 billion light-years. It is examining one of our near neighbours closely enough to distinguish different isotopes inside its atmosphere. The distance is short, the signal is difficult. That combination is scientifically important because the local neighbourhood is where the coldest brown dwarfs are easiest to characterise. Farther away, objects this faint disappear below our detection limits. So the coldest known brown dwarf may not be the coldest brown dwarf in the Milky Way. It is the coldest one, close enough and bright enough for us to study properly. There may be older objects that have cooled further. There may be lower mass objects. There may be genuine rogue planets with temperatures approaching those of Jupiter, or even colder. Some could have formed directly from collapsing gas. Others could have been ejected from planetary systems. Many would be extremely difficult to detect. Webb does not solve that population question by itself. What it gives us is the ability to understand the examples that surveys manage to find. And as those examples accumulate, the old boundary between stars and planets may become less useful as a single line, and more useful as a region. At the high mass end, ordinary stars sustain hydrogen fusion. Below them, brown dwarfs cannot. At lower masses, the deuterium burning distinction becomes uncertain and dependent on composition. Farther down, Objects can have clearly planetary masses regardless of whether they formed in a collapsing cloud or inside a disk. Atmospherically, the transition becomes even smoother. A cold brown dwarf and a giant planet may obey essentially the same molecular physics. The major difference can be history. WISE 0855 happens to sit near the point where all of these definitions begin overlapping. That makes its awkwardness valuable. If it fit comfortably into one category, there would be less reason to study it. Instead, it forces stellar astronomers and planetary scientists to work on the same object. One group may ask how far the star formation process can extend toward low masses. Another may ask how water clouds behave in a giant atmosphere at roughly 270 Kelvin. Another may use methane isotopes to constrain mass. Another may examine atmospheric mixing. Another may search for moons. All of them are looking at the same faint point. And that faint point has already changed considerably in our understanding without changing at all in reality. First, it was an unidentified infrared source. Then it became a fast-moving nearby object. Then the coldest known brown dwarf. Then a candidate with water clouds. Then a target with atmospheric variability. Then a Webb spectrum rich enough to reveal carbon monoxide, ammonia, water depletion, isotopic molecules, and unexpectedly little phosphine. Each new instrument has not replaced the object. It has replaced our incomplete view of it. That is probably the most useful way to think about WISE 0855 as we reach the end of this particular journey. It is not important because we need to decide whether it belongs in the star box or the planet box. It is important because it shows us where those boxes begin to fail. A star and a planet seem completely different when we compare the Sun with Earth. Move toward the smallest stars and largest planets, however, and the space between them becomes populated. Brown dwarfs fill much of that territory. Planetary mass brown dwarfs extend farther down. Rogue planets may overlap them. Cold white dwarfs such as WISE 0855 bring the atmospheric physics into almost direct contact with giant planet science. Webb is now showing us that transition molecule by molecule. The infrared spectrum does not contain a line marked star ends here. There is no sudden chemical feature saying planet begins. There is water condensing, methane absorbing, carbon monoxide being mixed upward, ammonia carrying isotopic information, phosphine appearing in surprisingly small quantities, internal heat escaping, gravity compressing the atmosphere, and behind all of it, an object with roughly planetary dimensions that has spent an enormous amount of time cooling in the darkness between stars. A little more than 7 light-years away, WISE 0855-0714 continues moving through the galaxy exactly as it did before anyone on Earth knew it existed. It does not know that WISE photographed it. It did not notice Spitzer measuring its parallax. Gemini collecting photons for hours made no difference to its atmosphere. Webb can examine water, methane, ammonia, carbon monoxide, phosphine, and isotopic molecules with remarkable precision, and WISE 0855 simply continues rotating, cooling, and releasing the small amount of internal heat it still carries. That may be the simplest fact to end with. This object was already there. We were the ones who finally learned how to notice it. For most of human history, the night sky was divided into things visible to our eyes and everything else. Stars were obvious. The moon was obvious. 5 planets could be followed as they moved among the stars. Later telescopes revealed fainter stars, moons around other planets, nebulae and galaxies. But even increasingly powerful optical telescopes would have struggled to show WISE 0855 because the problem was never just the size of the telescope. We needed to look in the right kind of light. Infrared astronomy gave us that ability. Once we did, an object that had been nearly absent from the visible sky became a nearby neighbour. That should make the darkness outside feel slightly less empty. Not crowded in any threatening sense. You do not need to check behind the curtains for a brown dwarf. WISE 0855 is still more than 7 light-years away, and it has shown no interest in visiting. But the spaces between the bright stars contain objects we could not have catalogued from visible light alone. Some are cold brown dwarfs, some may be free-floating planets, some are small enough and cold enough that current surveys have probably missed them unless they happen to pass reasonably close to us. The familiar stars are therefore only one part of our neighbourhood. WISE 0855 is an excellent reminder because it managed to remain undiscovered until 2014 despite being roughly 2.28 parsecs away. Even continued NEO-WISE measurements across more than a decade have been useful for refining something as basic as its infrared brightness, because the original observations were partly affected by a background source. There is something reassuringly ordinary about the way it was eventually understood. No spacecraft travelled there. No impossible new law of physics was required. Astronomers compared images. They noticed motion. They measured parallax. They collected infrared photons. Then they built better instruments and collected more. The great mystery gradually became a collection of measurements: distance, temperature, luminosity, spectrum, variability, molecular abundances. None of those measurements sounds particularly dramatic alone. Together they allow us to describe an atmosphere on an object more than 60 trillion kilometers away. That atmosphere turned out to be much busier than the word cold suggests. Water vapor is moving through it, at sufficiently cool heights that water begins leaving the gas phase through condensation. Webb's mid-infrared spectrum measures the resulting decrease in water vapor with altitude, even though the spectral signature of the water ice cloud particles themselves remains difficult to identify clearly. Methane is abundant. Ammonia is present strongly enough that Webb can distinguish a rare nitrogen isotope inside some of the ammonia molecules. Carbon monoxide survives in atmospheric regions where equilibrium chemistry would prefer methane, telling us that gas has been carried upward from hotter depths. Deuterated methane reveals a deuterium abundance consistent with an object low enough in mass to have avoided substantial deuterium destruction. Even phosphine, present at only about 1 part per billion in one recent retrieval, has become useful because its unexpectedly low abundance tells researchers that some piece of phosphorus chemistry remains incomplete. That is a considerable amount of activity for something we began by calling a frozen wanderer. Frozen remains useful as a comparison. WISE 0855 is extraordinarily cold compared with ordinary stars and nearly every previously known brown dwarf. But its atmosphere is not frozen solid. Its interior is not uniformly at room temperature. Heat still moves outward, gas still circulates. Pressure and temperature increase dramatically with depth. Chemistry changes from one layer to another. It is a functioning gaseous world, if we use world simply to mean a distinct astronomical body rather than a formal planetary classification. The word star requires even more care. The title, the coldest star in the universe, gives us an immediate way into the subject because WISE 0855 belongs to the family of star-like objects we call brown dwarfs. But after spending this much time with it, the reason for the qualification should be clear. WISE 0855 is not a true hydrogen-burning star. It does not shine because sustained nuclear fusion is operating in its core. It probably contains only several times the mass of Jupiter, far below the mass required for ordinary hydrogen burning. It began hot because gravitational collapse and contraction supplied energy, then spent its existence radiating that energy away. The cooling never stopped. That is how something formed through a star-like process could end up with an effective temperature of only a few hundred Kelvin. The result looks increasingly planetary as it ages. Its radius is around the scale of Jupiter. Its atmosphere contains molecules familiar from Jupiter. Its temperature overlaps with the range of cool giant planets. Water can condense. Methane dominates important parts of its carbon chemistry. Vertical mixing carries carbon monoxide upward. Its infrared brightness varies, probably because the atmosphere is not uniform, yet calling it a planet creates a different problem. Where is its star? Perhaps it never had one. The usual interpretation is that WISE 0855 formed independently, at the extremely low mass end of the same broad fragmentation processes that produce brown dwarfs. If that is correct, then it is not a planet that escaped from a system. It is an object that was born alone. But an ejected planet of similar mass and age might look extremely similar today. That ambiguity is not something we need to solve before going to sleep. Astronomers have not completely solved it either. There are useful definitions based on mass. There are definitions based on deuterium burning. There are definitions based on formation. Each works well in some situations and becomes uncomfortable in others. WISE 0855 happens to occupy exactly the part of nature where the discomfort becomes obvious. Perhaps that is why it has been so productive scientifically. A straightforward object confirms existing categories. An awkward object tests them. WISE 0855 has tested several. It challenged how cold astronomers expected the nearby brown dwarf population to become. It challenged atmospheric models designed for warmer objects. It encouraged comparisons with Jupiter. It pushed ground-based infrared spectroscopy toward its limits. Then Webb arrived and found enough information in its weak glow to challenge the chemical models again. We now know far more than we did at Discovery, but increased knowledge has not made the atmosphere boring. The questions have simply become more specific. Why is phosphine so scarce if mixing is vigorous? Exactly what kinds of water clouds form, and why are their predicted spectral signatures difficult to see? How does the temperature structure differ from a standard convective profile? What is the exact mass? How old is the object? How did it form? Does it possess moons? How quickly do its atmospheric structures change? Are there other objects even colder nearby? Those are questions for future observations. For tonight, the important point is that none of them requires WISE 0855 to be exotic in the sense of breaking known physics. Its strangeness comes from familiar physics operating under an unfamiliar set of conditions: gravity, gas pressure, thermal radiation, molecular absorption, convection, chemical reactions, condensation, rotation. The same basic laws that shape stars, planets, clouds, and laboratory gases on Earth also govern this dark object. Change the mass, remove the nearby star, wait billions of years. The outcome looks very different. That is one of the useful things about astronomy. The universe gives us experiments we could never construct ourselves. We cannot build a several Jupiter-mass ball of hydrogen and helium. We cannot place it in interstellar space. We cannot heat it during formation, leave it alone for a few billion years, then return to see what the atmosphere became. Nature has already run that experiment. WISE 0855 is one of the results. All we have to do is collect enough photons to read it. The photons reaching us tonight began their journey more than 7 years ago. If you're listening in 2026, the light arriving from WISE 0855 now left the object around 2019. While people on Earth were going to work, cooking dinner, missing buses, scrolling through phones and complaining about ordinary weather, infrared radiation was leaving a cold atmosphere around WISE 0855 and beginning its trip toward the solar system. Nothing about that radiation knew it would eventually reach a telescope. Most of it never will. The energy spreads outward in every direction. A tiny fraction crosses the path of Earth. An even smaller fraction enters one of our detectors. From that tiny sample, we reconstruct the whole object as best we can. If you think about it in practical terms, that should not work nearly as well as it does. We are not sampling the atmosphere directly. We are not watching individual weather systems. We cannot resolve the disk. We receive a point of infrared light. Yet spectroscopy tells us which molecules absorb which wavelengths. Astrometry tells us how the point moves. Parallax tells us how far away it is. Variability tells us the visible hemisphere changes as the object rotates. Evolutionary calculations connect its faintness with mass and age. Every technique takes a small indirect clue and turns it into one more piece of the physical picture. There is no single observation that tells the entire story. WISE 0855 has required a sequence of them. WISE first made the object noticeable in infrared survey data. Spitzer helped establish that it was nearby. Ground-based observatories pushed into wavelengths where enough thermal radiation escaped for spectroscopy. Long monitoring revealed variability. Webb expanded the spectrum until researchers could examine atmospheric chemistry in detail. The next major discovery may come from another instrument or simply from looking at the existing data in a better way. That is often how science works. Better hardware helps. Better models help too. So does noticing that an assumption everyone had been using does not fit the measurements anymore. WISE 0855 has supplied several of those moments. Perhaps years from now the object will no longer hold the record as the coldest known brown dwarf. Records in astronomy rarely last forever. A new infrared survey may find something colder, perhaps a very nearby object with an effective temperature much closer to Jupiter's, perhaps several. If that happens, WISE 0855 will not become less important. The first useful examples of a new regime often remain valuable because they gave astronomers the methods needed to understand what came later. Pluto stopped being the 9th planet and somehow survived the administrative disappointment. WISE 0855 can probably handle becoming the second coldest brown dwarf one day. For the moment, however, it remains our best studied example at this extreme, and because it is so close, it gives us a useful perspective on what nearby means in astronomy. 7 light-years feels enormous because human travel is slow. Voyager 1, one of the fastest objects humanity has sent out of the solar system, would require far longer than recorded human history to cover that distance at its present speed. So, WISE 0855 is not close in any practical travel sense, but the Milky Way is roughly 100,000 light-years across. Against that scale, 7 light-years is almost next door. Our local neighbourhood contains Alpha Centauri, Barnard's star, several faint red dwarfs, brown dwarfs, and now this extremely cold object that spent almost all of human history unnoticed. The neighbourhood is less obvious than the night sky suggests. Bright stars dominate because bright things are easy to see. They are not necessarily the most common or the most representative objects. Red dwarfs vastly outnumber sun-like stars. Brown dwarfs add another faint population. Free-floating planetary mass objects may add another. The galaxy could contain enormous numbers of bodies that contribute almost nothing to the familiar appearance of the sky. That thought does not require any dramatic conclusion. It simply means darkness is not the same thing as emptiness. If you happen to be near a window now, you could look outside and see whatever your local sky allows. Perhaps many stars, perhaps only a few because of city lights, perhaps clouds, perhaps nothing but the reflection of your own room. WISE 0855 would not be visible in any of those cases. You could know exactly where to look and still see nothing. That is appropriate in a way. The entire story has been about learning not to mistake visibility for existence. For thousands of years, WISE 0855 was absent from our maps. Then our maps improved. The object had not appeared. Our ability to detect it had. The same will happen again. Future surveys will find objects that current instruments miss. Some will be farther away. Some may be surprisingly close. Some may force astronomers to adjust classifications again. A few may occupy the same uncertain region between planet and brown dwarf. And each will make the local universe slightly less empty than it seemed before. So, before we finish, think back to where you were when we started. Perhaps not physically. Hopefully you have not moved very far if you're trying to sleep. But when WISE 0855 was first introduced, it was simply an unusually cold object, with an unpleasant catalogue name. Now that name carries quite a bit more information. WISE tells us how it was found. Its motion tells us it is nearby. Its faintness tells us how little energy escapes. Its spectrum tells us about water, methane, ammonia, carbon monoxide, phosphine and isotopes. Its temperature tells us how far brown dwarf cooling can proceed. Its low inferred mass places it close to the territory of giant planets. Its atmosphere gives us a laboratory for understanding worlds that future telescopes may eventually study around other stars. And its existence reminds us that an object can sit only 7 light-years away while remaining almost completely hidden from human vision. Where are you listening from tonight? And if you happen to know, what is the temperature outside where you are? It is a fitting question after spending this long with WISE 0855. Your answer may be warmer than parts of its atmosphere. It may even be colder on an especially severe winter night. That comparison is remarkable enough without embellishing it. An object formed through a star-like process has cooled until its atmospheric temperature overlaps with temperatures found on Earth. Not because someone turned it off, not because it suddenly froze, simply because it never had enough mass to sustain the hydrogen fusion of a normal star and has spent its lifetime gradually losing the heat with which it began. And if you found this long excursion into the colder part of our neighbourhood relaxing, you can leave a like, subscribe to Science for Sleep and share it with someone who might enjoy discovering that the space between the stars contains rather more than the visible stars would have us believe. For now, there is nothing more you need to measure. WISE 0855 will keep moving whether we watch it or not. Its atmosphere will keep circulating. Water will keep condensing where the temperature allows. Carbon monoxide will continue being carried upward. Infrared photons will continue leaving the object, crossing 7 light-years of space, and occasionally arriving at telescopes built by a species that did not even know this neighbour existed until very recently. You can leave the measurements to Webb. You can leave the classification argument to the astronomers. And somewhere beyond the visible stars, WISE 0855 can continue doing what it has probably done for billions of years, slowly releasing its remaining heat into space while the rest of the galaxy moves around it. Sleep well wherever you're listening from.